Look up at the night sky, and you might feel a sense of peace. The stars seem so permanent, so settled, but our solar system is anything but quiet. Beyond the familiar glow of the moon and the steady march of the planets, there are mysteries hiding in plain sight. Strange signals, unexplained movements, bewildering geological formations, phenomena that defy our best scientific explanations, and whisper of secrets we have yet to uncover. It's a cosmic backyard filled with more questions than answers, and today we're going to explore 25 of the most fascinating unexplained wonders right here in our own solar system. From the haunting hexagon raging at Saturn's North Pole to the bizarre behavior of objects at the very edge of our system, each of these phenomena challenges what we think we know. Some might be natural oddities waiting for the right discovery. Others hint at something even more extraordinary. They remind us that for all our telescopes and probes, there is still so much we don't understand, and perhaps that's the most exciting part of being human. This journey isn't just about listing strange occurrences. It's about diving into the heart of curiosity itself, exploring the edges of knowledge where science meets wonder. So come with us as we travel from the sun-scorched surface of Mercury to the icy realms beyond Neptune. We'll uncover lingering enigmas on Mars, delve into the chaotic terrain of distant moons, and confront signals and sights that even experts struggle to explain. This is more than a tour of the unknown. It's an invitation to see our neighborhood in space with fresh eyes, to marvel at how much remains hidden just next door. Let's begin. Our journey begins with a structure so precise, so geometrically perfect, it seems almost artificially crafted. Hovering over Saturn's North Pole is a colossal hexagon, a six-sided jet stream wider than two Earths placed side by side. This isn't a fleeting cloud formation. It's a persistent, swirling vortex that has endured for decades, perhaps even centuries, defying the turbulent chaos of the planet's atmosphere. Imagine a hurricane, but one locked into a sharp, angled shape with sides each longer than the diameter of our entire planet, spinning in a dizzying dance that completes a full rotation roughly every 10 hours and 30 minutes. The sheer scale is incomprehensible. A weather pattern of such monumental proportions, it challenges our very understanding of how fluids and gases behave under extreme conditions. What makes this hexagon so baffling to planetary scientists isn't just its existence, but its stability. In our experience, nature tends toward curves and randomness, not sharp angles and rigid symmetry. Turbulent atmospheric systems on Earth, like our own jet streams, are meandering and irregular. Yet here on Saturn, we see a perfect geometric shape maintaining its form relentlessly amidst swirling winds that scream past at over 300 miles per hour. It's a paradox of chaos and order happening on a planetary scale. The Cassini spacecraft provided our most stunning visuals of this wonder, its cameras capturing the hexagon in various wavelengths of light, revealing a deep-rooted structure that extends hundreds of kilometers down into the cloud tops, with a massive, churning storm sitting directly at its center. So how does such an impossible structure form and persist? Scientists have turned to laboratories and supercomputers to find answers, simulating the dense, hydrogen-rich atmosphere of the gas giant. One leading theory suggests it's a manifestation of a standing wave pattern, a kind of stable oscillation in the atmosphere, much like how a wave can appear to stand still in a fast-moving stream. Other models point to deep-rooted differences in wind speeds at various latitudes, creating shear forces that somehow organize themselves into this polygonal shape. It's possible the hexagon is a vast, self-organizing system, a natural product of deep atmospheric dynamics that we simply haven't observed anywhere else. This isn't just a curiosity, it's a natural laboratory that, if understood, could rewrite textbooks on fluid dynamics and planetary meteorology. It serves as a profound reminder that the universe often holds patterns far stranger and more wonderful than anything we could invent. From one gas giant's atmospheric puzzle, we travel inward to our planetary neighbor, a world often called Earth's twin but with an environment straight out of a nightmare. Venus presents us with another profound atmospheric mystery, one that moves at a dizzying, almost violent pace, while the planet itself takes 243 Earth days to complete a single, agonizingly slow rotation on its axis. Its thick, toxic atmosphere has a mind of its own. High above the scorching surface, hurricane-force winds scream around the entire planet at speeds surpassing 200 miles per hour, completing a full circle in a mere 4 Earth days. This phenomenon, where the atmosphere rotates up to 60 times faster than the solid planet below, is known as superrotation, and it turns our basic understanding of planetary weather completely on its head. On Earth, our weather systems are fundamentally coupled to the planet's rotation. The spin of the Earth drives our jet streams and ocean currents, creating a system that moves largely in sync. Venus shatters this model. It's as if the entire crushing atmosphere has become unglued from the planet it envelops, creating a perpetual planet-wide hurricane that never loses its fury. This isn't a localized storm, but a single, cohesive weather system engulfing the entire globe, a feat of atmospheric mechanics that has no equal in our solar system. Probes like the Japanese Akatsuki orbiter have mapped these winds in stunning detail, showing a smooth, unbroken flow that races from the day side to the night side with terrifying efficiency, homogenizing the planet's incredibly hostile climate. The mechanisms that drive and sustain this incredible engine are the subject of intense debate. One prevailing theory points to thermal tides. Venus's incredibly dense atmosphere, mostly carbon dioxide, acts like a massive heat sink. The Sun's immense heating on the day side creates tremendous pressure differences, and as the hot air rises, it pulls cooler air from the night side along with it. This constant, global-scale circulation might be transferring the Sun's energy into the atmosphere's momentum, effectively giving it a push. Another fascinating idea involves something called atmospheric waves, large-scale ripples and oscillations generated by the flow over surface features like mountains. These waves could be transporting energy from the lower, slower atmosphere up to the cloud tops, accelerating the high-altitude winds in a continuous feedback loop that keeps the superrotation locked in place. Yet, despite these plausible explanations, full-scale computer simulations consistently struggle to replicate the ferocity and stability of Venus's superrotation. The models either can't get the winds to spin fast enough or they can't maintain the system over geological timescales. This tells planetary scientists that a key ingredient is still missing from our recipe. Perhaps it's a complex interaction between the solar heat, the chemistry of the sulfuric acid clouds, and the strange surface conditions where temperatures are hot enough to melt lead and the pressure is 92 times that of Earth's at sea level. Venus's superrotation is more than just a curious weather pattern. It is a stark lesson in humility. It shows us that even on a planet so close to us, the fundamental principles that govern fluid dynamics and energy transfer can operate in ways we are only beginning to comprehend. Leaving the thick, swirling atmosphere of Venus behind, we arrive at our next destination, a world that has captivated humanity's imagination for centuries, Mars. The red planet presents a mystery that cuts to the very heart of our search for life beyond Earth, and it comes in the form of a simple gas, methane. Here on our own planet, the vast majority of atmospheric methane is produced by biological processes, by living organisms like microbes, or by the decay of organic matter. So when our robotic explorers on Mars began sniffing out whiffs of this gas, the scientific community was understandably electrified. The Curiosity rover, our most advanced mobile laboratory on the Martian surface, has been meticulously analyzing the air inside Gale crater for years, and its data tells a story that is both compelling and deeply puzzling. It has detected not just a constant, low background level of methane, but also occasional, sudden, and dramatic spikes where the concentration of the gas skyrockets by up to 60 times before vanishing again almost as quickly as it appeared. These aren't random events, they follow a pattern. Curiosity's long-term monitoring has revealed a clear seasonal cycle to the background level of methane, with peaks occurring during the late summer in the Martian northern hemisphere and troughs in the winter. This predictable ebb and flow suggests a large-scale process tied to the planet's climate, perhaps the annual thawing of shallow subsurface ice releasing trapped gas. But the sudden, massive spikes are a different beast entirely. They appear unpredictably and dissipate within a single Martian day, hinting at an incredibly localized and recent source, possibly somewhere just upstream from the rover's path. The short lifespan of methane in the Martian atmosphere is a critical part of this puzzle. Ultraviolet radiation from the sun and chemical reactions in the air should break the methane molecules apart within a few hundred years. Therefore, any methane we detect today must have been released very recently, pointing to an ongoing, active process happening somewhere beneath the rusty soil. This is where the great debate ignites, splitting the mystery into two captivating possibilities. The first and most thrilling is biology. Could these methane burps be the signature of subterranean Martian microbes, tiny organisms living in aquifers deep below the frozen surface, producing methane just as their counterparts do on Earth? It's a tantalizing thought that the first evidence of extraterrestrial life might be a ghostly trace of gas that appears and vanishes before our instruments. The second, more probable but no less fascinating explanation is geology. Mars is a geologically active world, and processes like serpentinization, a reaction between water, carbon dioxide, and certain types of rock like olivine, can produce methane abiotically without any need for life. Hotspots of subsurface volcanic activity, even if not producing surface lava flows, could also be heating rocks and releasing trapped ancient methane from reservoirs deep within the planet. The controversy deepens when we bring another player into the story: the Trace Gas Orbiter, a European spacecraft circling Mars with instruments specifically designed to map atmospheric gases at a global scale. Intriguingly, and to the frustration of many, the orbiter has so far failed to detect any of these large methane spikes that Curiosity sees from the ground. This discrepancy isn't a case of one instrument being wrong, it's a clue. It suggests that the methane releases are extremely localized and brief, perhaps contained within the crater itself or released at night and destroyed by the time the orbiter passes overhead. Solving the methane riddle is arguably one of the most crucial goals in modern planetary science. If the source is geological, it reveals a more dynamic and complex Martian interior than we ever suspected. But if it is biological, it would represent a discovery that would fundamentally reshape our understanding of the universe and our place within it. This isn't just about finding a gas, it's about chasing the ghost of a possibility, a potential whisper of life on the world next door. While Mars teases us with the possibility of hidden life, Jupiter presents a spectacle of pure, awe-inspiring power that has been visible for centuries. This is the Great Red Spot, a colossal anti-cyclonic storm so vast that the entire Earth could be swallowed within its swirling crimson jaws with room to spare. What is truly staggering is not just its size but its age. This single storm system has been raging continuously since at least the 1600s, when astronomers first trained their primitive telescopes on the gas giant. Imagine a hurricane on Earth that began during the time of Shakespeare and has been spinning relentlessly ever since, outliving every human empire, every scientific revolution, and every war. That is the profound timescale we are dealing with, a monument to persistence in a universe of constant change. For generations, we watched this titanic storm from afar, assuming it was a permanent fixture of Jupiter's chaotic atmosphere. But recent observations have revealed a startling new chapter in its long life. The Great Red Spot is shrinking. Measurements taken over the past century show it has been steadily contracting, and while it still dwarfs our planet, it is now perhaps only a third of the size it was a little over 100 years ago. Its once oval shape is also becoming more circular, and its iconic reddish hue has been deepening, occasionally shifting to a more orange palette. This transformation poses a critical question. Are we witnessing the slow death of a solar system legend, or merely a new phase in its immensely long life? The storm's winds, however, show no signs of weakening, still screaming around its periphery at speeds exceeding 250 miles per hour, a testament to the immense energies at play. So what fuels this ancient tempest, allowing it to defy the atmospheric friction and turbulence that would cause a storm on any other planet to sputter out in a matter of days or weeks? The secret lies in Jupiter's very nature. Unlike Earth, Jupiter has no solid surface to disrupt atmospheric flow and sap a storm's energy through friction. This means there's no landmass to break the storm apart. It simply spins freely in the boundless, fluid atmosphere. More importantly, Jupiter is a powerhouse of internal heat. The planet is still contracting under its own immense gravity, and this process generates tremendous thermal energy from within, which it radiates back into its atmosphere. This internal heat, combined with the fierce energy it absorbs from the sun, creates a colossal engine of convection. It's this constant, violent churning hot gases rising, cooling, and sinking that provides a near-limitless source of energy to feed and sustain mighty storms like the Great Red Spot. Our understanding of this legendary storm has been revolutionized by NASA's Juno spacecraft, which has been conducting breathtakingly close flybys since 2016. Juno's suite of instruments has peered deep beneath the cloud tops, revealing that the Great Red Spot is not a shallow weather feature. It is a behemoth that plunges hundreds of miles down into the planet's atmosphere, much deeper than anyone had previously estimated. This incredible depth is likely another key to its longevity, anchoring it firmly within the complex layers of Jupiter's atmospheric currents. Juno's cameras have also captured stunningly detailed images of the storm's chaotic interior, showing a tangled web of darker, warmer clouds swirling at its core and brighter, colder clouds spinning around its outer edge, a complex structure that we are only beginning to decode. The Great Red Spot stands as a stark contrast to the fleeting storms we see on other worlds. Neptune, for example, also boasts a giant dark spot, but observations from Voyager 2 and the Hubble Space Telescope showed that feature had completely vanished within just a few years. The difference highlights just how unique the conditions on Jupiter are, providing the perfect nursery for a storm that could become a permanent resident. Whether the Great Red Spot continues to shrink until it eventually winks out of existence, or whether it stabilizes and enters a new, compact phase of its multi-century life, remains one of the most captivating questions in planetary science. It is a humbling reminder of the dynamic and powerful forces that shape the gas giants, forces that operate on a scale and a time frame that is almost impossible for the human mind to fully comprehend. Yet for all its destructive power, the Tunguska Event left behind a perplexing void, no crater. The epicenter of the blast shows a radial pattern of flattened trees, all pointing outward from a central point, but that point itself is not a hole in the ground. Instead, it is a stand of strangely skeletal trees, stripped of their branches but still standing upright. This complete absence of any significant impact crater is the central puzzle that has fueled decades of scientific debate and wild speculation. It tells us that the object itself never actually struck the Earth. Instead, it unleashed its entire colossal energy in a cataclysmic airburst, an explosion in the sky between 3 and 6 miles above the surface. The resulting shockwave was like a gigantic hammer blow from the heavens, transferring immense force straight down into the forest below without leaving a traditional crater. So what was this object, and why did it explode with such violence? The most widely accepted theory points to a small asteroid, or more likely, a comet. A rocky asteroid entering the atmosphere at hypersonic speeds would experience tremendous pressure and heat on its leading surface. If it was particularly fragile or entered at a shallow angle, it might not have had the structural integrity to remain intact all the way to the ground. The immense stresses could have caused it to fragment and then explode violently in a flash of thermal and kinetic energy. A comet composed of icy material and dust is an even more fragile candidate. As it screamed through the atmosphere, the icy nucleus would have heated up almost instantaneously, causing it to vaporize in a massive detonation equivalent to a multi-megaton bomb. This theory neatly explains the lack of a crater and the widespread peculiar damage on the ground. However, the absence of any sizable fragments has also given rise to more exotic explanations. In the 1970s, some physicists suggested the culprit could have been a tiny black hole, no larger than an atom but with the mass of a large asteroid, passing straight through the Earth and exiting out the other side, releasing a shockwave of energy as it entered and exited the atmosphere. While a captivating idea, this theory has largely been dismissed due to a complete lack of any supporting seismic evidence or a corresponding exit event in the North Atlantic. Another fringe idea proposed an explosion of natural gas leaking from the ground, but this fails to account for the object witnessed flying through the sky by numerous eyewitnesses. The leading scientific consensus remains firmly planted in the cosmic impactor camp, but the exact nature of that impactor is still refined with new research. Recent scientific expeditions to the Tunguska site have used modern technology to search for clues that earlier explorers might have missed. By analyzing sediment cores from the peat bogs in the blast zone, researchers have found microscopic particles and enrichments of elements like iridium, which is rare on Earth's surface but common in asteroids and comets. They've also discovered nanodiamonds and tiny spheres of fused glass and metal, all potential fragments of the vaporized body. In 2020, a study even proposed that the blast was caused by an iron asteroid that grazed the atmosphere, skipping off the upper layers like a stone on a pond and releasing its energy in a fiery airburst without ever fully impacting. This grazing impact theory adds another fascinating layer to the possible scenarios. Ultimately, the enduring importance of the Tunguska event extends far beyond historical mystery. It serves as a stark and sobering warning. If such an airburst were to occur today over a densely populated metropolitan area, the results would be catastrophic, leveling a city and causing unimaginable loss of life. This is why Tunguska is a fundamental cornerstone of planetary defense studies. It provides a real-world data point on the effects of a medium-sized impact event, helping scientists model the potential damage and formulate strategies for detection and deflection. It is a dramatic reminder that the solar system is a dynamic shooting gallery, and Earth is not always a bystander. The empty crater at Tunguska is not evidence that nothing happened. It is proof that sometimes the greatest threats come from the sky itself, delivering their devastating payload without ever touching the ground. Shifting our gaze from the storm-racked giants, we arrive at the innermost planet, a world of extremes that defies our expectations in a much quieter, yet equally profound way. Mercury, a scorched and cratered rock barely larger than our moon, presents a mystery that comes from deep within its heart, a global magnetic field. This might not sound as visually dramatic as a giant storm, but for planetary scientists it is a shocking discovery. Based on everything we thought we knew, Mercury should be geologically dead, a solid, frozen relic whose small size would have allowed its internal heat to escape into space billions of years ago. Without that churning, molten interior, a magnetic field should be impossible. Yet, the Mariner 10 spacecraft first detected this faint magnetic shield in the 1970s, and decades later, NASA, a messenger mission, confirmed it was real, throwing a massive wrench into our models of how small, rocky planets live and die. So how does this small world generate this protective bubble? The answer lies in its most dominant feature, something hidden beneath the surface, a colossal iron core. Mercury is a planetary overachiever when it comes to metal. Its core is enormous, making up a staggering 85% of the planet's radius. To put that in perspective, Earth's core is only about half of its radius. This means Mercury is essentially a giant ball of iron with a relatively thin shell of rock draped over it. This massive core is the potential engine for the magnetic field. The leading theory for generating planetary magnetic fields is the dynamo effect, the idea that the convective motion of a swirling, molten, electrically conductive material like iron can generate a global magnetic field, much like a bicycle dynamo creates electricity. Earth's powerful field is generated by its molten outer core. The puzzle with Mercury is that its core, given the planet's small size, should have cooled and solidified completely eons ago, shutting down any hope of a dynamo. This is where the Messenger mission transformed our understanding. By meticulously mapping Mercury's gravity field and measuring its rotational spin, the spacecraft revealed a critical detail: the core is not entirely solid. A portion of it is still molten. This was the crucial clue, but it immediately created a new and more complex puzzle. If there's a liquid outer core, why is the resulting magnetic field so remarkably weak? Mercury's field is only about 1% as strong as Earth's. A classic active dynamo like our own should produce something much stronger. This paradox forced scientists to reconsider the entire engine room of the planet. One compelling new theory suggests this isn't a full-powered dynamo at all, but something far more delicate. It's possible that the very top layer of the liquid outer core is slowly crystallizing onto the solid inner core beneath it. As this iron snow falls, it creates subtle movements and chemical buoyancy that could generate just enough of a current to produce the faint magnetic field we observe. It's a weak, dying dynamo running on its last legs. Another fascinating idea points to the planet's extreme elliptical orbit. Mercury's journey around the Sun is a wild ride, bringing it incredibly close and then swinging it far away. This constant gravitational tug of war with the Sun exerts massive tidal forces on the planet, much like the Moon's pull on Earth's oceans. Some models show that these tidal forces could be vigorously stirring the molten core, providing an extra source of energy to keep the convective motions going and supplementing the weak thermal energy left over from the planet's formation. Messenger's data also delivered a final surprise. The magnetic field is not centered on the planet's core. It is significantly offset to the north by about 20% of Mercury's radius. This lopsided field suggests that the dynamo process is happening in an unusual way, perhaps constrained by the strange geometry of the core mantle boundary or influenced by the uneven cooling of the planet. The implications of this small, stubborn magnetic field reach far beyond Mercury itself. It forces us to rewrite the story of planetary formation and evolution. How did Mercury end up with such a massive metal core? One leading theory suggests a colossal impact in the early solar system might have blasted away most of its original rocky mantle, leaving behind the dense, metal-rich heart we see today. Its persistent, weak magnetism also tells us that small planets can hold onto their internal heat and geological activity in surprising ways for much longer than we ever anticipated, operating on a different set of rules than their larger cousins. Understanding Mercury's magnetic heart is like finding a faint, steady pulse in a place we assumed was long dead. It is a profound lesson in humility, reminding us that even the smallest, most seemingly simple worlds can hold onto deep and complex secrets, challenging our assumptions at every turn. But our journey from the scorched plains of Mercury leads us to a world that is the polar opposite, a place where water, not rock, is the defining feature. We arrive at Jupiter's moon Europa, an ice-clad orb that looks more like a cracked marble floating in the void. For decades, scientists have been captivated by the possibility that a global, liquid water ocean, more than twice the volume of all Earth's oceans combined, sloshes beneath its frozen crust. This alone makes Europa one of the most promising places to search for life beyond our planet. But the mystery here isn't just what lies beneath, it's what occasionally erupts from within. Europa has been caught shooting giant plumes of water vapor hundreds of miles into space, offering us a free sample of its hidden sea and a tantalizing shortcut in our search for alien biology. The first hints of this incredible activity came from the Hubble Space Telescope, which in 2012 observed what appeared to be faint, transient auroras at Europa's south pole. The best explanation for these glows was that charged particles from Jupiter's powerful magnetic field were interacting with molecules of water, breaking them apart. This suggested that Hubble wasn't seeing the moon's surface, but was instead looking right through giant geysers of water erupting into the vacuum. Later observations, particularly in 2013 and 2016, seemed to confirm this stunning reality. Hubble's instruments detected the distinct ultraviolet signature of water molecules being broken apart by sunlight, pinpointing these events to the same general region near the moon's equator. These weren't constant fountains, but rather sporadic, enormous outbursts, like a pressure cooker occasionally blowing its lid and venting its contents into space. The implications of this discovery are nothing short of revolutionary for astrobiology. Europa's subsurface ocean is thought to be in contact with a rocky seafloor, heated by the immense tidal forces generated by Jupiter's gravity. This constant flexing and squeezing of the moon's interior likely keeps the water liquid and could drive hydrothermal vents on the ocean floor, environments that on Earth are teeming with life completely independent of sunlight. If microbial life, or something even more complex, has evolved in those dark, salty depths, then the organic molecules, salts, and perhaps even microorganisms themselves could be carried upward through the ocean and ejected into space within these plumes. This means we might not need to drill through miles of ice to find evidence of life. A spacecraft could simply fly through one of these plumes, sample the ejected material, and analyze it on the spot. This is precisely the breathtaking opportunity that NASA's upcoming Europa Clipper mission is designed to seize. Scheduled to arrive at Jupiter in the 2030s, Clipper is not a lander. It is a sophisticated orbital laboratory built for this exact purpose. Its suite of instruments includes mass spectrometers that can identify complex organic molecules and dust analyzers that can catch tiny grains of ice ejected from the plumes. The mission plan involves making nearly 50 close flybys of Europa, and mission planners will be using data from Hubble and other telescopes to potentially target these flights through active plume regions. It's a bold strategy to taste the ocean of another world without ever touching down. However, the plume phenomenon is not without its controversy. Subsequent observations, including a dedicated campaign with Hubble, have struggled to consistently replicate those initial detections. Some attempts have seen nothing, leading to questions about whether the plumes are rare, have specific triggers, or if we are sometimes misinterpreting the data. This uncertainty adds a thrilling element of a treasure hunt to the Clipper mission. It may have to hunt for these elusive geysers, using its powerful cameras and thermal instruments to look for warm spots on the ice or subtle surface changes that betray a recent eruption. The very elusiveness of the plumes tells us that their activity is tied to complex factors, perhaps linked to the moon's orbital position and how much it is being stretched by Jupiter's gravity at any given moment. Whether the plumes are a constant feature or a rare event, their existence points to a dynamic and active world. the energy required to blast water through a crust of ice that is potentially miles thick is immense, suggesting powerful geologic forces are at work beneath the surface. This isn't a dead, frozen block. It's a living world with a heart that periodically beats, sending its lifeblood out into the solar system. For scientists, Europa's plumes are the most inviting backdoor into an alien ecosystem we have ever discovered. They represent a chance to answer one of humanity's oldest questions, are we alone, by simply reaching out and catching a piece of another world as it leaps up to meet us. And now we journey from the watery plumes of a distant moon to a silent, listening post here on Earth, where a single burst of noise from the cosmos became one of the most tantalizing and enduring mysteries in the history of astronomy. It was the evening of August 15, 1977, at Ohio State University's Big Ear radio telescope. This massive instrument was part of the humble beginnings of the search for extraterrestrial intelligence, or SETI, scanning the skies for any signal that stood out from the natural background static of the universe. For years, the telescope's output was a monotonous string of numbers and letters representing the faint hiss of empty space. But on this night, volunteer researcher Jerry Amon was reviewing the previous night's computer printout when his eye caught something that made his heart stop. There, amidst a sea of alphanumeric code indicating negligible signal strength, was a sequence of 6 characters, 6EQUJ5. It represented a narrowband radio signal so powerful, so unprecedented, that Amon circled it in red pen and wrote next to it a single, breathless word that would give this event its name forever: wow. The signal itself was a marvel of precision. It lasted for exactly 72 seconds, the exact duration the Big Ear telescope could focus on a fixed point in the sky as the Earth rotated. It blasted in at a frequency of 1,420 MHz, which is profoundly significant. This frequency is part of a protected band called the water hole, a quiet region of the radio spectrum where background noise from the universe is at a minimum. It is also the emission frequency of neutral hydrogen, the most common element in the cosmos. Scientists had long theorized that an advanced civilization might choose this universal, quiet frequency to broadcast a cosmic hello, as it would be a logical channel for any species attempting to communicate across the interstellar void. The signal's intensity profile was also perfect. It rose and fell in a smooth, symmetrical curve as it passed through the telescope's twin horns, exactly as would be expected from a distant, point-like source beyond our solar system. The immediate and obvious question was, and remains, what was it? The characteristics screamed of an artificial origin. It was narrowband, meaning all its power was concentrated on one specific frequency, unlike the broadband noise of natural cosmic objects like pulsars or quasars. It came from a specific point in the constellation Sagittarius, near the Chi Sagittarii star group, with no known stars or planets in the immediate vicinity. The hunt was on to find it again. Over the decades, numerous projects using far more sensitive and advanced radio telescopes have repeatedly pointed back toward that same patch of sky. They have scanned that frequency and millions of others around it, listening for a repeat performance. Despite all this effort, the signal has never been heard again. Not a whisper, not a blip. Its one-time-only appearance is the central pillar of its mystery. This silence has forced scientists to search for natural, one-off explanations. One of the most prominent theories, proposed in 2017 by astronomer Antonio Paris, pointed the finger at a pair of passing comets. The idea was that the comets, named 266P/Christensen and 335P/Gibbs, which were in the vicinity at the time, have large clouds of hydrogen gas surrounding them. As this hydrogen might emit radiation at around the 1,420 MHz frequency, it could have created a temporary, powerful signal as they moved through the Big Ear's field of view. However, this hypothesis has been largely dismissed by the broader astronomical community. Subsequent analysis showed that the comet's hydrogen clouds are far too diffuse to generate such an intense narrowband signal, and the frequency emitted by cometary hydrogen is actually slightly different from the exact frequency of the WOW signal. The timing and positions also didn't align perfectly with the original observation. Other natural explanations have been floated. It could have been an unusual burst of radio emission from a passing asteroid or a previously unknown astrophysical phenomenon. Perhaps it was a reflection of a human-made signal bouncing off a piece of space debris, a discarded satellite booster, or a chunk of wreckage temporarily creating a blinding glint of radio light in the telescope's receiver. The problem with all these terrestrial explanations is that our own radio transmissions are usually easy to identify. They are messy, spread across many frequencies, and often traceable back to a known source. The WOW signal was remarkably clean, appearing on only one channel with a purity that is incredibly difficult to achieve accidentally. The original computer printout, with its red circle and exclamation, is now a sacred relic in the history of science, a testament to a moment of pure, unadulterated potential. It sits at the heart of a philosophical debate. Was it our first and best candidate for a message from another star, a fleeting sign that we are not alone? Or was it merely an incredibly rare and still unknown natural event, a cosmic mirage that perfectly mimicked what we hoped to find? The signal's enduring power lies in its ambiguity. It is a Rorschach test for our hopes and our skepticism. For SETI researchers, it is both a beacon of encouragement and a lesson in patience, a reminder that the universe is vast and our listening has only just begun. It tells us that if there are other voices out there, they may not be broadcasting continuously on a schedule we can predict. They might be whispering, and we must be listening at exactly the right moment to hear them. Leaving behind the silent mystery of a potential signal from the stars, we now turn to a world where the evidence of powerful, unseen forces is written across its atmosphere in furious, dark storms. As we venture to the outer solar system, we arrive at Neptune, the windiest planet in our cosmic neighborhood, where supersonic gales race around the globe and mysterious dark vortices appear and vanish like ghosts. But the true enigma of this brilliant blue ice giant lies not in what we see on its surface, but in what we detect emanating from within. Despite being the planet farthest from the Sun, receiving only a faint whisper of solar energy, Neptune is a powerhouse of internal heat, radiating about 2.6 times more energy than it absorbs from our star. This is a profound and puzzling imbalance of energy that has profound consequences for the planet's chaotic weather and challenges our understanding of how giant planets cool down over billions of years. To grasp why this is so strange, we need only look at its near twin, Uranus. Both planets are similar in size, mass, and composition. Both are ice giants, composed largely of water, ammonia, and methane ices surrounding a rocky core. They formed in the same region of the early solar system and should have similar internal histories. Yet, when the Voyager 2 spacecraft flew past them in the 1980s, it made a startling discovery. Uranus is thermally dead, radiating away almost exactly the same amount of energy it gets from the Sun. Its internal heat flow is negligible. Neptune, on the other hand, is practically boiling over with excess energy. This fundamental difference is one of the great unsolved puzzles in planetary science. Why is one ice giant so energetically active while the other is dormant? The answer seems to lie in the violent and chaotic processes that shaped their infancy. The most widely accepted explanation for Neptune's fierce internal heat is that it is the leftover thermal energy from its formation over 4.5 billion years ago. As countless planetesimals, chunks of rock and ice crashed together to form the nascent planet, each impact released a tremendous amount of gravitational energy, effectively hammering the young world into a molten, intensely hot ball. For a giant planet like Neptune, this initial heat budget is colossal. The subsequent 4.5 billion years have been a continuous process of this primordial heat slowly leaking out from the deep interior, rising through the layers of fluid and gas, and finally radiating into the icy cold of space. The mystery is not that Neptune still has heat to lose, but that it has managed to retain so much of it for so long, while Uranus seemingly lost its birth heat completely and rapidly. This is where the theories diverge into fascinating possibilities. One compelling idea is that a colossal impact early in Uranus's history may have fundamentally altered its destiny. A cataclysmic collision with an Earth-sized protoplanet could have knocked Uranus onto its side, giving it its extreme 98-degree axial tilt. Such a massive blow might have also effectively scrambled the planet's interior, stirring it so violently that the internal heat was released in one giant, rapid burst, leaving the planet thermally depleted. Neptune, perhaps spared such a violent trauma, may have been able to retain its heat and release it in a slow, steady simmer over the eons. Another theory points to differences in their internal structures. Even small variations in the distribution of heavier elements and rock could affect how efficiently heat is transported from the core to the upper atmosphere. Neptune's interior might be structured in a way that inhibits cooling, perhaps through layered convection where different strata of the atmosphere don't mix easily, creating a kind of insulating blanket that traps the heat inside. The effects of this internal furnace are written plainly across Neptune's dynamic atmosphere. This is not a quiet, cold world. The extra heat rising from below acts as a powerful engine, driving the most extreme weather system in the solar system. It creates tremendous convection currents, forcing plumes of warm gas to rise rapidly through the colder upper atmosphere. This constant churning is the primary driver behind those supersonic winds, which have been clocked at speeds exceeding 1,200 miles per hour. It also fuels the formation of giant, Earth-sized storm systems like the Great Dark Spot observed by Voyager 2, a massive anti-cyclonic storm similar to Jupiter's Great Red Spot. Unlike the storms on gas giants closer to the Sun, which are primarily powered by solar energy, Neptune's storms are largely driven from within. This internal heat source means the planet's weather has a powerful and consistent energy supply, making it incredibly violent and unpredictable even by the standards of the outer solar system. Modern observations from telescopes like the Keck Observatory and the Hubble Space Telescope continue to monitor Neptune's thermal emissions, using sophisticated infrared cameras to map heat distribution across its disk. These thermal images reveal a surprising fact. The planet's equator is actually cooler than its south pole, which is currently tilted toward the Sun. This is completely counterintuitive, as we would expect the region getting the most sunlight to be the warmest. But on Neptune, the internal heat flow is so significant that it overwhelms the weak influence of solar heating, creating a temperature profile that is dictated from the inside out. This is a stunning demonstration of just how powerful this internal engine really is. It fundamentally controls the climate of the entire planet, making Neptune a world whose vibrant, turbulent character is shaped not by the distant Sun, but by the fiery heart it has carried since the very dawn of the solar system. After exploring the fiery heart of Neptune, we arrive at one of the most visually striking and geologically bizarre worlds in the entire solar system, Saturn's moon Iapetus. From a distance, it looks almost artificial, like a giant cosmic walnut or a piece of carefully crafted machinery. Its most shocking feature is a monster of a mountain range, a continuous ridge that runs with near-perfect precision along its equator, stretching over 800 miles long and soaring to heights that dwarf Mount Everest, reaching up to 12 miles high in some places. This is the equatorial ridge, a feature so unique and so improbably placed that it has fueled scientific debate and wild speculation since its discovery, a true one-of-a-kind wonder with no parallel on any other known moon or planet. The first clues to Iapetus's strangeness came long before we could see its details. The moon has a profound two-tone coloration, a yin-yang of brilliant white and deep space black. Centuries ago, the astronomer Giovanni Cassini noted he could only see Iapetus on one side of Saturn. It would vanish when it swung around to the other side. We now know why. One hemisphere, the leading side as it orbits Saturn, is covered in a dark, reddish material as black as fresh asphalt, while the trailing hemisphere is blindingly bright, covered in pristine water ice. This dark material absorbs sunlight, warming that side of the moon just enough to cause ice to sublimate, to turn directly from a solid into a gas. This gas then migrates across the moon and refreezes onto the colder, bright side, creating a runaway feedback loop that has intensified the contrast over billions of years, painting one half of the world in shadow and leaving the other in light. But the ridge remains the central enigma. How does a natural geological process produce a feature so perfectly aligned with the equator, so symmetrical, and so astonishingly large? For a moon only 900 miles in diameter, a 12-mile high ridge is a Himalayan-scale feature on a body a third the size of our moon. The most prominent theory suggests that Iapetus was once a much faster spinner. Early in its history, it may have completed a full rotation on its axis in just a handful of hours. This rapid spin could have generated immense centrifugal force, forcing the moon to bulge significantly at its equator. As its rotation gradually slowed due to gravitational tides from Saturn, this frozen-in bulge might have collapsed, buckling inward and upward to form the massive ridge we see today, a permanent fossilized record of its youthful energy. A competing and equally fascinating theory posits that Iapetus may have once possessed its own ring system, a thin, elegant disk of debris encircling the moon. Over time, this ring would have become unstable, and its particles would have gently rained down onto the moon's surface. Because of the laws of orbital dynamics, this material would have been naturally funneled to settle along the gravitational contour of the equator, piling up in a narrow band that eventually grew into a towering ridge of icy rubble. This theory elegantly explains the ridge's precise alignment, but it immediately raises another difficult question. How would a small moon like Iapetus have acquired rings in the first place? Perhaps it suffered a giant impact that blasted material into orbit, a cataclysm whose only remaining evidence is this bizarre equatorial necklace. The Cassini spacecraft's flybys in the 2000s provided our most stunning close-ups, and the images are breathtaking. The ridge isn't a single, smooth wall. It is complex, rugged, and deeply scarred, with individual peaks standing in stark relief against the blackness of space. In some regions, it appears almost like a chain of mountains that have merged together, while in others, it looks like a single, sheer cliff face cutting the moon in two. Topographic maps built from Cassini data reveal that the ridge is not perfectly uniform. It has gaps and variations in height, but its overall fidelity to the equator is uncanny. These details make the collapse or ring debris theories more plausible than any sort of internal tectonic activity, which would be unlikely to produce such a symmetrical and localized feature. What makes Iapetus truly special is its solitude in this regard. In all our exploration of the solar system, we have found nothing else like this equatorial ridge. Other moons have mountains and cracks and vast plains, but none have a global equatorial wall that seems to divide the world into two hemispheres. Its uniqueness suggests that its formation required a very specific and rare combination of circumstances, a rapid initial spin, a particular composition, and just the right orbital history to preserve the feature once it formed. It stands as a monument to the incredible diversity of geological processes at work in our solar system, processes we are still struggling to categorize and understand. Iapetus is a puzzle box floating in the void, its ridge a constant challenge to our understanding of how worlds are built and how they evolve. Venturing even further out into the frigid darkness beyond Neptune, we find ourselves in a region known as the Kuiper Belt, a vast donut-shaped ring of icy debris that is the source of many of our solar system's comets. For years, astronomers have been meticulously mapping this distant realm, cataloging thousands of these frozen leftovers from the solar system's formation. Their sizes and distribution were expected to follow a predictable pattern, gradually thinning out the farther one travels from the Sun. But the data has revealed something deeply puzzling, a boundary so abrupt it seems to defy the natural order of our cosmic neighborhood. Around 50 astronomical units from the Sun, that's 50 times the distance from Earth to the Sun. The number of Kuiper belt objects doesn't just gently decline, it plummets. This is the Kuiper cliff, a sudden and dramatic drop-off in objects that marks what appears to be the effective edge of our classical solar system, and its existence is one of the most compelling hints that a major piece of our planetary puzzle is still missing. The most tantalizing and headline-grabbing explanation for this artificial-looking boundary is the potential existence of a yet undiscovered planet, a so-called Planet 9 or Planet X. The theory posits that a massive world, perhaps 5 to 10 times the size of Earth, could be orbiting the Sun hundreds of astronomical units away on a highly elliptical path. The gravitational influence of such a colossal object would act like a cosmic shepherd, its immense pull clearing out a vast swath of space by either ejecting smaller objects from the solar system entirely or shepherding them into orbits that are tilted and clustered in a way we haven't yet fully observed. This would neatly explain not only the Kuiper cliff, but also the strange, clustered orbits of a handful of extreme trans-Neptunian objects that seem to be herded together by some unseen force. The gravitational signature required to create these effects points toward a true planetary body lurking in the perpetual twilight of the outer solar system. However, the scientific community is rightly cautious, and other, less sensational explanations are actively being explored. The most significant of these is simple observational bias. It is extraordinarily difficult to detect small, dark objects at such incredible distances. The Kuiper cliff could represent not a true physical edge, but the limit of our current technological ability to see. Our surveys are inherently biased toward finding larger, brighter objects, and it's entirely possible that a population of smaller, fainter Kuiper belt objects exists beyond 50 astronomical units, waiting for more powerful telescopes to reveal them. Another compelling theory reaches back into the solar system's violent infancy. The grand migration of the giant planets, particularly Neptune's outward journey, could have dynamically sculpted the outer disk, scattering a huge number of objects inward and leaving behind a sharply truncated population at the edge. This ancient gravitational clearing could have created a fossilized edge that has persisted for billions of years. This is where NASA's A New Horizons mission becomes a critical detective in this cosmic mystery. After its historic flyby of Pluto, which sits right around that crucial 40 to 50 astronomical unit mark, the spacecraft has continued its journey into the deepest reaches of the Kuiper belt. It has already provided stunning close-up views of the Kuiper belt object Arakoth, a primordial, untouched relic that looks like two pancakes stuck together, offering a glimpse into the building blocks of the solar system. As New Horizons travels farther out, its cameras are constantly scanning the space around it, not just for new flyby targets, but to directly measure the density of small, faint objects in this frontier region. By counting the number of tiny objects it can detect along its path, the spacecraft is conducting a direct census that is free from the biases of Earth-based telescopes. If it finds that the population of small objects remains abundant beyond 50 astronomical units, it will strongly suggest the cliff is an illusion of our limited technology. But if its data confirms the steep drop-off, the case for a massive perturbing object, a true Planet 9, becomes exponentially stronger. The search for this potential planet is a painstaking process that involves some of the world's most powerful telescopes, like the Subaru Observatory in Hawaii. Astronomers are methodically scanning the sky, looking for a single, incredibly faint, slow-moving dot of light against a backdrop of millions of fixed stars. It is a needle in a haystack search of epic proportions, but modern digital sky surveys and sophisticated data processing techniques are making it increasingly feasible. Whether the Kuiper cliff is ultimately explained by a distant giant world or by the subtle echoes of our solar system's formation, its very existence forces us to reconsider the boundaries of our own celestial backyard. It is a stark reminder that our maps of the solar system are still incomplete, and that profound discoveries likely await in the darkness just beyond the edge of everything we currently know. Yet even on our own familiar moon, a world we have walked upon and mapped in exhaustive detail, there are patterns of such exquisite and delicate beauty that they seem almost painted onto the surface by an invisible hand. These are the lunar swirls, some of the most visually stunning and scientifically perplexing features in the entire solar system. Appearing like ethereal, cream-colored brushstrokes across the dark gray lunar regolith, these bright, swirling patterns can stretch for hundreds of miles across the moon's surface, their intricate, cloud-like forms standing in stark contrast to the heavily cratered terrain that surrounds them. The most famous of these, Reiner Gamma, is so prominent it can be spotted with a backyard telescope here on Earth, a luminous comma-shaped smudge on the ocean of storms that has captivated astronomers for centuries. For generations, we assumed they were simply unusual volcanic deposits or the results of some impact-related phenomenon, but data from modern orbiters has revealed a truth far more fascinating and complex. The first major clue to their origin came with the discovery that these beautiful swirls are not just surface decorations. They are intimately linked to powerful, localized magnetic fields. While the moon lacks a global magnetic shield like Earth's, it does possess these strange, isolated pockets of magnetism known as magnetic anomalies. When scientists from missions like NASA's, a Lunar Prospector Orbiter, overlaid maps of these magnetic fields onto images of the swirls, the correlation was astonishing. The bright, swirling patterns align almost perfectly with the strongest of these anomalies. It appears the magnetism and the bright swirls are two sides of the same coin, different manifestations of a single underlying phenomenon. This discovery immediately shifted the entire investigation, turning a geological puzzle into a magnetospheric one, and pointing toward an interaction between the lunar surface and the harsh environment of space itself. The leading theory that has emerged from this is as elegant as it is compelling, and it involves a constant, invisible barrage from the sun. Our star continuously emits a flood of charged particles known as the solar wind, a supersonic stream of mostly protons and electrons that screams through interplanetary space. This wind has a profoundly darkening effect on the moon's surface. Over billions of years, these particles bombard the lunar soil, a process called space weathering that breaks down the crystalline structure of minerals and implants tiny particles of iron nanospheres, gradually turning the bright, reflective lunar soil into a darker, redder, more subdued landscape. This is why young, fresh craters appear bright white. Their ejected material hasn't been exposed to this long-term darkening process, while older terrain is much darker. But what if something was protecting the swirls from this ceaseless bombardment? This is where the magnetic anomalies come in. Scientists propose that these localized magnetic fields, though not strong enough to shield an astronaut, are perfectly capable of acting as a miniature magnetic umbrella for the soil beneath them. As the charged particles of the solar wind approach the moon, these magnetic bubbles deflect them, bending their paths away from the protected surface and funneling the damaging radiation around the edges of the anomaly. The result is a natural preservation effect. The soil within the magnetic swirl remains immature, its bright, reflective qualities preserved from the day it was first exposed, while the surrounding terrain continues to be slowly and steadily darkened by the solar wind. Over millions of years, this creates the stark, beautiful contrast we see from orbit. The swirls are essentially time capsules of brighter regolith, their patterns mapping the invisible lines of magnetic force that shield them. However, this elegant deflection theory isn't without its own complications and competing ideas. Some researchers point out that not every magnetic anomaly on the Moon has a corresponding swirl, and not every swirl is perfectly shielded. This suggests that the strength and geometry of the magnetic field are crucial, and that the deflection might not be 100% efficient. Another fascinating hypothesis involves cometary impact. This theory suggests that a comet's small, weak magnetic field, carried along with its flowing coma of gas and dust, could have temporarily magnetized the lunar crust at the moment of a low-angle grazing impact. The impact itself would have scoured the surface and exposed fresh, bright soil, while the transient magnetic field it generated became frozen into the shocked, heated rocks below, creating a permanent magnetic anomaly that then began deflecting solar wind and preserving the bright patch it created. This could explain the swirling, tendril-like shapes which resemble patterns made by other types of glancing impacts. The evidence gathered by NASA, a lunar reconnaissance orbiter, has been crucial in weighing these options. LRO's powerful cameras have shown that the soil within the swirls isn't just brighter. Its spectral properties are different, with a much higher reflectance and a distinct lack of the spectral signatures associated with space weathering. The orbiter has also found that the swirl regions are not topographically distinct. They are not hills or depressions, but exist on the same level as the surrounding terrain, ruling out the idea that they are deposits of different material. They are the same material, simply preserved in a more pristine state. The mystery deepens when we consider that these magnetic anomalies are likely remnants of a time, over 3 billion years ago, when the Moon did have a global magnetic field generated by a churning molten core. As that field died away, these small, intensely magnetized patches of crust may have been all that remained, their magnetism locked into the rocks during ancient volcanic eruptions that created iron-rich deposits like those in the lunar Maria. Ultimately, the lunar swirls represent a beautiful and fragile dance between a world and its star, an interaction where invisible magnetic forces paint visible patterns on a global canvas. They are a testament to the dynamic nature of what we often mistake for a dead, static world. Understanding them isn't just about solving a lunar puzzle, it has profound implications for future exploration. If we can master the principles of these natural magnetic shields, we might one day be able to generate artificial versions to protect lunar outposts from the harmful effects of solar and cosmic radiation, using the Moon's own tricks to help us live on its surface. They stand as a reminder that even on our closest celestial neighbor, mysteries of breathtaking elegance are still waiting to be fully understood, their secrets hidden in plain sight. Leaving behind the painted swirls of our Moon, we plunge deeper into the asteroid belt to a world that is itself a category of one, Ceres. The largest object in that vast ring of debris between Mars and Jupiter, Ceres is a 500-mile-wide dwarf planet that was, for a long time, little more than a faint speck of light in our telescopes. That all changed in 2015 when NASA's Dawn spacecraft arrived and began its orbital dance, revealing a world pockmarked with craters and holding one of the most visually arresting mysteries in the solar system. As Dawn approached, its cameras captured something utterly bewildering, a cluster of intensely bright spots glaring from the darkness of the 80-million-year-old Ocata crater, shining with the brilliance of distant headlights on a dark highway. These weren't subtle features, they were dazzling, defiantly bright beacons against the otherwise dark, carbon-rich surface of the dwarf planet, and their discovery immediately launched a frantic scientific quest to understand what on Earth, or rather, off Earth, could be causing them. The Dawn mission's suite of instruments was perfectly poised to solve the puzzle. Its visible and infrared mapping spectrometer analyzed the light reflecting from these brilliant spots, breaking it down into a spectral signature that acts like a chemical fingerprint. The results were stunning and unequivocal. The primary material making up these bright deposits was sodium carbonate, a kind of salt commonly found in evaporite deposits on Earth, like the breathtakingly white landscapes of Death Valley. This was a monumental discovery. While carbonates had been spotted on other worlds, never before had they been found in such quantity and purity, forming vast, concentrated deposits that act like a brilliant white mirror reflecting the weak sunlight. Mixed in with this sodium carbonate was a sprinkling of ammonium chloride, another compound that hints at a complex and intriguing chemical history for this small world. The sheer reflectivity or albedo of these spots is what makes them so eye-catching. They are among the brightest natural features in the entire solar system, a stark white scar on a world of muted grays. The immediate and obvious question was how these vast salt flats came to be exposed on the surface. The leading theory and the most compelling narrative that has emerged from the dawn data points to a process of cryovolcanism, ice volcanism. But this isn't the fiery, magma-spewing kind we know on Earth. On a cold world like Ceres, the magma is a cold, salty mud, and the force driving it upward is not heat from radioactive decay but the stubborn persistence of liquid water refusing to freeze. Scientists believe that the impact that created Ocata crater billions of years ago was a catastrophic event that didn't just dig a hole. It fractured Ceres's crust to its very core, creating deep faults and weaknesses that tapped into a hidden reservoir. Deep beneath the surface, Ceres is now believed to harbor a global or regional brine reservoir, a vast aquifer of salty water kept liquid by the antifreeze properties of dissolved salts, and perhaps a residual amount of heat from the dwarf planet's formation. This is where the story gets dynamic. The impact-generated fractures provided a conduit for this deep, salty brine to percolate upward. Once it reached the colder, near-vacuum conditions of the surface, the water would have rapidly sublimated, turning directly from a solid into a gas, vanishing into space and leaving behind only the non-volatile salts and minerals it had carried in solution. It's a process akin to the salt crust that forms when a puddle of seawater evaporates on a hot day, but happening on a planetary scale over millions of years. Dawn's high-resolution images of the crater show a breathtakingly complex landscape that supports this idea. The central brightest area, named Cerealia Facula, sits in a pit suggesting a past eruption site. Surrounding it is a fractured, domed floor, indicating that the ground has been pushed upward from below by the upwelling of material. This is not a static landscape. It is the frozen record of a recent, and perhaps even ongoing, geological tantrum. The evidence suggests this wasn't a one-time event. The Dawn mission's data indicates that the bright deposits are relatively young, with the central dome being perhaps just a few million years old. This points to a multi-stage process. The initial impact may have triggered a massive, immediate upwelling of brine. Later, as the fractures remained open, smaller, more episodic eruptions could have continued, periodically refreshing the bright deposits and preventing them from being darkened by the constant rain of dark dust from meteorite impacts across the asteroid belt. The presence of the ammonium chloride is another critical clue. Ammonium is not a common compound in the inner solar system, but it is plentiful in the frigid outer reaches. Its presence on Ceres suggests the dwarf planet may have formed much farther out in the solar system, perhaps beyond Neptune, before migrating inward to its current home, carrying with it the chemistry of its cold birthplace. The discovery of Ceres's bright spots and their briny origin fundamentally transforms our view of this small world. It is no longer just a large asteroid. It is a geologically active ocean world in miniature. The existence of a deep, liquid brine reservoir makes Ceres one of the most compelling places in the solar system to look for habitable environments, as liquid water is the one non-negotiable ingredient for life as we know it. While Ceres itself may be too cold and its chemistry too harsh for life, The processes at work there, the movement of water, the concentration of organic molecules, and the energy released by impacts and chemistry are a masterclass in the ways small bodies can remain dynamic billions of years after their formation. The brilliant lights of Okata crater are not a passive reflection. They are a beacon pointing toward a hidden, watery interior, a vivid announcement that even in the cold, dark depths of the asteroid belt, there are worlds with stories still unfolding. But the persistence of this alien cycle presents a fundamental chemical conundrum. Solar ultraviolet radiation is relentless, and on Titan, it acts like a cosmic scalpel, constantly breaking apart methane molecules in the upper atmosphere. The math is starkly simple. Based on the rate of this photochemical destruction, all the methane currently in Titan's atmosphere should have been completely stripped away and converted into heavier hydrocarbons within a mere 10 to 20 million years. Given that Titan is as old as the solar system itself, this means the methane we see today cannot be the original supply. It must be actively and continuously replenished from a hidden reservoir. The lakes and rivers we observe are merely the visible part of a much deeper system, the fleeting surface expression of a world struggling to maintain its unique identity against the erasing power of sunlight. The breathtaking cycle we witness is therefore not a closed loop but a leaky one, demanding a faucet somewhere beneath the surface that is slowly turning to keep the entire system from draining dry. This brings us to the central mystery. What is the source? Where is this hidden wellspring that defies the sun's destructive power? Planetary scientists have two primary suspects, each with compelling evidence. The first is a vast subsurface reservoir of liquid methane, a kind of alien aquifer trapped within a porous layer of water ice and rock deep beneath the frozen crust. This theory suggests that Titan's crust behaves like a giant, icy sponge, soaking up liquid hydrocarbons that occasionally seep up to the surface to feed the lakes or perhaps even erupt in massive outpourings. The second and more dynamic suspect is cryovolcanism. Instead of spewing molten rock, a Titanian cryovolcano would erupt a slushy mix of liquid water and ammonia, acting as a deep underground elevator that transports methane from a buried ocean up to the surface. As this watery lava reached the frigid surface, the methane would be released as a gas, venting into the atmosphere to begin its cycle anew. The data from the Cassini mission provides tantalizing hints for both ideas. The spacecraft's radar mapper revealed a landscape that looks remarkably familiar yet utterly alien, with shorelines, river deltas, and islands that are sculpted not by water, but by liquid methane and ethane. Some of the larger northern lakes, like Krakenmare, have incredibly sharp, steep rims that suggest they are filled by underground springs rather than rainfall alone, much like a terrestrial sinkhole. Furthermore, Cassini's observations of the surface over time revealed a few transient bright spots features that appeared and then vanished, which some researchers interpreted as possible evidence of an erupting cryovolcano, a brief burp of material from the interior. However, conclusive proof has remained elusive, and the debate over the primary replenishment mechanism is far from settled. What makes Titan's methane cycle so profoundly significant is that it is the only other known world with a complex, active hydrological cycle, even if its working fluid is methane instead of water. This presents us with an incredible natural laboratory for studying climate and geology under a completely different set of rules. Titan has its own clouds, its own rain, its own rivers, and its own lakes. It experiences evaporation, condensation, and precipitation, driving erosion and shaping its surface in ways that are deeply familiar to us. Yet, the differences are just as instructive. Because methane is less viscous than water and Titan's gravity is weaker, its rivers are wider, shallower, and more meandering than those on Earth. Its rainfall is likely a slow, gentle drizzle of large droplets falling through a thick, hazy sky. Studying these parallels and divergences helps us understand the universal principles of fluid dynamics and climate science. principles that could apply to countless worlds orbiting other stars. And now we journey from the complex chemistry of distant moons to the silent, steady flight of humanity's first emissaries to the outer planets. As the Pioneer 10 and 11 spacecraft completed their historic missions to Jupiter and Saturn, they continued on a one-way trip into the abyss, becoming the first human-built objects destined to leave our solar system entirely. For decades, these robotic pioneers dutifully phoned home, their faint signals tracked by NASA, a deep space network with breathtaking precision. But as scientists meticulously analyzed their trajectories, they noticed something deeply unsettling. Both spacecraft were experiencing a tiny, unexplained, and constant deceleration back toward the Sun. This was the Pioneer anomaly, a subtle cosmic drag that defied explanation for over 30 years and threatened to upend our fundamental understanding of physics. The effect was incredibly small, measured at about 8.74 times 10 to the negative 10th meters per second squared. To put that in human terms, it's equivalent to the gravitational pull you'd feel from a single grain of sand held in the palm of your hand. Over the vast distances of space travel, however, this minuscule push adds up. Over the course of a year, it would cause a spacecraft to drift off its predicted course by about 5,000 kilometers. After a decade, that error ballooned to nearly 50,000 kilometers, a significant deviation that demanded an explanation. This wasn't a sudden glitch. It was a persistent, unidirectional force acting on the probes, a gentle but mysterious tug backwards that seemed to contradict the known laws of orbital mechanics governed by Einstein and Newton. The immediate and most thrilling possibility was that we had stumbled upon new physics. Could this be evidence of a flaw in our theory of gravity, a hint that Einstein's general relativity needed modification at the largest scales? Some theorists proposed exotic ideas, including the influence of dark matter, the gravitational pull from unseen matter in the solar system, or even the existence of extraspatial dimensions subtly altering the force of gravity over immense distances. The idea that a 40-year-old spacecraft could be the key to a scientific revolution captured the public imagination and sent physicists scrambling for their chalkboards. The Pioneer anomaly became a classic scientific detective story, a puzzle hiding in plain sight within decades of telemetry data. The painstaking search for an answer was a monumental effort in forensic engineering. A dedicated team of researchers, led by Slava Turyshev, spent years recovering old data stored on archaic formats like magnetic tapes and even printouts, poring over the original engineering blueprints to understand every possible source of a mundane on-board effect. They had to account for everything from the gravitational pull of the Kuiper belt to the pressure of the solar wind. The ultimate breakthrough came not from looking outward into the cosmos, but by looking inward at the spacecraft's own design. Pioneer 10 and 11 were powered by radioactive thermoelectric generators, or RTG, which produced heat that was converted into electricity. The spacecraft themselves were asymmetrical, with the large, dish-shaped high-gain antenna acting as a sunshade for the body of the probe. The team developed a sophisticated thermal model of the spacecraft and realized that the heat emitted by the onboard electronics and the RTGs was not radiating away symmetrically. More heat was being emitted from the back of the antenna dish, which faced toward the sun, than from the sides. According to the simple physics of thermal radiation, photons carrying away this heat also carry a tiny amount of momentum. The uneven radiation created a net recoil force, a gentle but constant push that was directed back toward the sun, perfectly mimicking an anomalous deceleration. When this complex thermal model was applied to the decades of trajectory data, the anomaly vanished almost entirely. The mysterious force was, in the end, the spacecraft braking against its own heat. While the thermal recoil explanation is now widely accepted as the primary cause, a sliver of the original mystery persists for some. The meticulous analysis showed that the thermal model accounts for the vast majority of the anomalous acceleration, but a tiny, residual signal. A few percent of the original effect might still remain unaccounted for. This has led to suggestions that other minor factors, like the slight leakage of propellant from the attitude control thrusters or the way radio waves exert a tiny pressure on the large antenna, could explain the remainder. For most of the scientific community, the case is closed. The Pioneer anomaly was a spectacular lesson in how the intricate details of engineering can masquerade as revolutionary physics. It stands as a testament to the incredible precision of our deep space tracking and the painstaking diligence required to understand the data it provides. The implications of this solved mystery are profound for future space exploration. It underscores the critical importance of understanding a spacecraft's thermal environment and the potential for unintended side effects from its own power systems. For missions requiring ultra-precise navigation, such as those searching for gravitational waves or making detailed maps of gravitational fields around other planets, even the faintest push from thermal radiation must be meticulously modeled and accounted for. The decades-long saga of the Pioneer anomaly is a humbling reminder that before we invoke new laws of the universe, we must first ensure we have fully understood the laws of our own machinery. It is a story that celebrates not a revolutionary discovery, but the power of meticulous, long-term scientific investigation to find the truth hidden in the data. And now we turn to one of the most profound and bizarre architectural flaws in our solar system's design. While every other planet spins more or less upright like a top on a table, Uranus has been completely knocked over. It rotates on its side with an extreme 98-degree axial tilt, meaning its poles point almost directly toward the Sun at the solstices, while its equator is plunged into darkness. This isn't a slight wobble. It's a full-scale planetary reorientation that dictates every aspect of its existence, from its mind-bending 42-year-long seasons to the strange behavior of its magnetic field. The prevailing theory for this cosmic catastrophe is as dramatic as the tilt itself, a colossal impact with an Earth-sized protoplanet in the early, violent days of the solar system. Imagine the scene billions of years ago. The young solar system was a chaotic construction zone filled with planetary embryos jostling for space. In this orbital demolition derby, a proto-Uranus was likely sideswiped not once but twice by a massive object. The most sophisticated computer simulations suggest a series of grazing collisions were more probable than a single, head-on strike. These impacts would have been utterly cataclysmic, delivering an unimaginable amount of energy. The first blow might have set the planet spinning rapidly, and a second strike delivered at just the right angle could have delivered the final shove that toppled the world onto its side. The debris from this violent encounter would have been thrown into orbit, eventually coalescing to form Uranus's system of moons and narrow rings, all of which now orbit around its tilted equator, tracing its new, sideways rotation like a set of celestial hula hoops. This extreme tilt has staggering consequences for the Uranian climate, creating the most extreme seasonal cycle of any planet. A single orbit around the Sun takes Uranus 84 Earth years. This means each season, spring, summer, autumn, and winter, lasts for 21 years. During the summer solstice at a pole, the Sun does not set for 21 straight years. It hangs in the sky, circling overhead in a tight spiral, baking one hemisphere in perpetual daylight. Meanwhile, the opposite pole is plunged into a 21-year-long night of absolute deep freeze darkness. Then, as the planet continues its slow journey, the roles reverse. At the equinoxes, the Sun passes over the equator, providing something closer to a normal day-night cycle for a brief period, with each rotation taking about 17 hours. This bizarre pattern likely creates incredibly lopsided atmospheric circulation, with heat struggling to move from the sunlit pole to the frozen, dark side, a climate system we are only beginning to model. The mysteries don't stop with the seasons. Uranus's magnetic field adds another layer of profound weirdness. Unlike Earth's field, which is roughly aligned with our rotational axis, Uranus's magnetic field is tilted by a staggering 59 degrees from its rotational axis. Even more bizarrely, the field is not centered on the planet's core. It is significantly offset, as if the magnetic engine is located closer to the surface. This creates a magnetic environment around Uranus that is unlike any other, a complex and lopsided magnetosphere that tumbles wildly through space as the planet rotates. Scientists believe this peculiar magnetic field is generated not by a dynamo in a molten iron core, as on Earth, but by the motion of a super-dense, superheated, and electrically conductive ocean of water, ammonia, and methane ices deep within the planet. The giant impact that tilted Uranus may have also severely disrupted the flow of this interior ocean, leaving its magnetic field permanently askew. This immediately raises a compelling question: why is Uranus the odd one out? Its near twin in size and composition, Neptune, has a much more conventional 28-degree axial tilt. Why did one ice giant suffer such a traumatic history while the other emerged relatively unscathed? The answer likely lies in the chaotic and random nature of the early solar system. The migration of the giant planets, particularly Jupiter and Saturn, is thought to have sent gravitational shockwaves through the disk of planetesimals, scattering countless large objects on erratic paths. It's possible Uranus simply found itself in the wrong place at the wrong time, directly in the path of one or two of these planetary wrecking balls. Neptune, forming just a bit farther out, may have been shielded from the worst of the chaos, or perhaps it experienced its own giant impacts that were less effective at tilting the entire world, instead affecting its moon system or internal structure in ways we haven't yet detected. The tilted nature of Uranus makes it a unique laboratory for understanding planetary formation and climate dynamics. Its extreme seasons force us to refine our models of atmospheric heat transport and energy balance under conditions we can never experience on Earth. Its off-kilter magnetic field challenges our fundamental understanding of how dynamos operate within fluid planetary interiors. Every strange detail we learn about this sideways world provides a critical data point, helping us interpret the countless exoplanets we are discovering around other stars, many of which may have similarly dramatic axial tilts. Uranus stands as a permanent monument to the violence of planetary birth, a world forever frozen in the aftermath of a primeval collision, reminding us that the serene clockwork of the solar system was forged in an era of incredible cosmic violence. But if we look even closer to the very surface of our star, we find a paradox so profound it has challenged solar physicists for the better part of a century. This is the mystery of the corona, the sun's wispy, ethereal outer atmosphere that is visible during a total solar eclipse as a magnificent pearly white crown. It seems intuitive that the farther you get from a heat source, the cooler things become. If you stand near a campfire, you feel the most heat right next to the flames, not several feet away. The sun defies this basic logic in the most spectacular way. The visible surface of the sun, the photosphere, is a searing 5,500 degrees Celsius. Yet, just a few thousand kilometers above it, in the thin plasma of the corona, the temperature skyrockets to an unimaginable 1 to 2 million degrees Celsius. This means the sun's outer atmosphere is hundreds of times hotter than its surface, a finding that is as baffling as discovering a flame is cooler than the air surrounding it. For decades, the central question has been simple yet monumental. What incredible engine is pumping immense heat into the corona against this seemingly impossible thermal gradient? The prime suspect in this cosmic whodunit is the sun's own magnetic field, a chaotic and dynamic web of invisible force lines that governs virtually all solar activity. The surface of the sun is not a calm, solid ball. It is a roiling sea of plasma, a superheated gas of charged particles. This plasma is constantly churning, and as it moves, it drags the sun's magnetic field lines with it, twisting them, stretching them, and tying them into complex knots of immense magnetic energy. Think of it like stretching a rubber band or winding up a spring. You are storing potential energy that is suddenly released when you let go. On the Sun, this stored energy is released in a process called magnetic reconnection, a fundamental but explosive process where magnetic field lines snap, break, and reconfigure themselves into a more stable shape. When this happens, the colossal magnetic energy that was stored in the twisted fields is converted almost instantaneously into thermal and kinetic energy, violently heating the surrounding plasma and sometimes even catapulting it out into space as a solar flare or a coronal mass ejection. While large, dramatic flares are the most visible sign of this activity, many scientists now believe the true key to the coronal heating problem lies in events far too small and frequent for us to easily see. This is the nanoflare theory proposed by physicist Eugene Parker. His revolutionary idea was that the corona isn't heated by a few gigantic explosions, but by an uncountable number of tiny, nano-sized flares popping off all over the sun every second of every day. Each individual nanoflare would be minuscule, but their collective, continuous energy release could provide the steady, immense heat needed to keep the corona at millions of degrees. It's the difference between trying to heat a room with a single, massive bonfire that roars and then dies versus heating it with trillions of microscopic sparks going off constantly. Confirming this theory has been a monumental challenge because these proposed nanoflares are incredibly faint and happen on scales too small for most telescopes to resolve, leaving them as a compelling but elusive explanation for decades. This is where a new generation of solar observatories is changing the game. NASA Parker Solar Probe is on a historic mission, performing a series of daring close passes through the corona itself, flying closer to the Sun than any spacecraft in history. Its goal is not just to observe the corona from a distance, but to fly directly into it, to taste the solar wind and measure the electric and magnetic fields in the region where the heating is actually happening. Think of it as sending a weather plane directly into the eye of a hurricane to understand its power, rather than just watching it from satellite images. Parker's initial data has already been revelatory, revealing a zone of intense magnetic activity and plasma turbulence near the Sun that perfectly matches what scientists would expect from an environment powered by constant magnetic reconnection events, both large and small. Simultaneously, the Daniel K. Inouye Solar Telescope on the ground is providing the highest resolution images of the solar surface ever taken, allowing us to see the magnetic field's fundamental building blocks in stunning detail, potentially capturing the tiny magnetic knots that could be the seeds of those theorized nanoflares. Solving this mystery is far more than an academic exercise. It is crucial for protecting our technology-dependent civilization. The superheated corona is the source of the solar wind, a constant stream of charged particles that flows outward through the solar system. The processes that heat the corona also accelerate this wind to tremendous speeds and, more critically, generate the solar storms that can wreak havoc on Earth. These storms are born from the sudden release of energy through magnetic reconnection. If we can finally understand the precise mechanisms that heat the corona and trigger these explosive events, we can dramatically improve our space weather forecasting models. This would give us vital advance warning, not just days but potentially weeks, to protect astronauts from radiation, safeguard orbiting satellites that manage our communications and GPS, and harden power grids on Earth against crippling geomagnetic-induced currents. The quest to solve the coronal heating problem is a fundamental journey to understand our star, but it is also a practical mission to secure our future in space and on Earth. Leaving behind the scorching mysteries of our Sun's corona, we travel millions of miles to a small, doomed world circling the red planet Mars. This is Phobos, a lumpy, potato-shaped moon that is one of the strangest objects in our solar system, and it is covered in a pattern so peculiar it looks almost artificial. Across its surface, stretching for miles, are precise, parallel grooves, a series of long, linear valleys and ridges that carve straight across craters and other obstacles with an unnerving geometric regularity. For decades, since the first clear images were beamed back by the Viking orbiters in the 1970s, these grooves have been a subject of intense debate. Are they the scars of a colossal impact, the stretch marks of a world being slowly torn apart, or something else entirely? These are not random cracks. They are a systematic inscription on the Moon's surface, a message about its violent past and its inevitable future. The most straightforward explanation, and the one that held sway for many years, points to a massive crater on Phobos itself. This is Stickney, an impact scar so large it dominates one entire end of the Moon, a gaping wound that likely came perilously close to shattering Phobos completely. The immense force of the impact that created Stickney would have sent powerful seismic shockwaves racing through the small Moon's interior. Because Phobos is only about 17 miles across and lacks any significant gravity to pull itself into a firm, spherical shape, its structure is likely a loose pile of rubble barely held together, what scientists call a rubble pile. The theory suggests that the grooves are chains of secondary craters, formed by boulders and debris blasted out from the Stickney impact, rolling and bouncing across the surface in straight lines, or they could be fractures opened up by the seismic shaking itself, a network of faults created in a single catastrophic event. However, as our imagery has improved, particularly with stunning high-resolution photos from NASA, a Mars reconnaissance orbiter, this simple story has begun to unravel. The pattern of the grooves is almost too perfect, too globally organized to be the result of a single local impact. Many of the grooves are aligned along the tidal axis, the imaginary line pointing directly toward Mars. This has led to a more dynamic and terrifying theory, that the grooves are not ancient scars but the live-action evidence of Phobos' ongoing destruction. Mars's gravity exerts a powerful tidal force on its small moon, and because Phobos orbits faster than Mars rotates, those tidal forces are actually pulling the Moon inward, closer to the planet with each passing century. This relentless pull is putting incredible stress on Phobos, stretching and squeezing it, and many scientists believe the grooves are the surface expression of this tidal stress, stretch marks forming on a world that is being literally pulled apart. Sophisticated stress model visualizations show that the predicted patterns of fracturing from this tidal stretching match the observed alignment and distribution of the grooves with startling accuracy, suggesting we are watching a moon in its death throes. This leads to a dramatic prediction about the future. The same forces creating these grooves are sealing the Moon's fate. In an estimated 30 to 50 million years, the tidal stresses will become too great and Phobos will cross the Roche limit, the distance where a planet's gravity overwhelms the self-gravity of a satellite. When that happens, Phobos will be completely dismantled. It will not crash into Mars in one piece. Instead, it will fracture into a million pieces, creating a magnificent, temporary ring of debris around the red planet that will then slowly rain down upon its surface over subsequent millions of years. The grooves, therefore, are not just a record of a past impact. They are the cracks in the ceiling, the first signs of a catastrophic structural failure happening in extremely slow motion. We are witnessing the beginning of the end for a moon, a process that will culminate in a planetary spectacle unseen for billions of years in our solar system. The mystery of Phobos' grooves is a perfect example of how a single, strange feature can open a window into the fundamental forces that shape worlds. Whether they are primarily the result of Stickney's ancient violence or the ongoing tidal forces that will one day destroy the Moon, they tell a story of a fragile, captured asteroid living on borrowed time in a gravitational tug-of-war it cannot win. Each new mission proposed to Phobos, whether to land on its surface or observe it from orbit, has solving this puzzle as a top priority. By studying the mineralogy within the grooves, measuring their depth, and mapping their exact orientation, we can finally determine their true origin. Phobos is a unique natural laboratory for understanding the processes of tidal disruption, offering us a front-row seat to a cosmic demolition project that unfolds over epochs, its progress etched in perfect parallel lines across a dying world. Yet beyond the fragile, fractured reality of Phobos, we cast our gaze outward, past the orbits of all the known planets, past the Kuiper belt, and into the deepest, darkest void surrounding our solar system. Here, in that profound emptiness, lies the most extensive and least understood structure humanity has ever theorized, the Oort cloud. This is not a cloud you could see or touch. It is a vast, spherical shell of icy planetesimals believed to encase our entire solar system like a colossal, invisible cage. Its scale is so immense it defies everyday comprehension. While the Kuiper belt might be the solar system's attic, the Oort cloud is its ultimate frontier, a distant, frozen reservoir that marks the absolute edge of the sun's gravitational influence and the source of some of our most spectacular celestial visitors. The evidence for this enigmatic cloud is entirely indirect, a brilliant piece of cosmic detective work built upon the predictable paths of long-period comets. These are the comets that arrive from every conceivable direction in the sky, with orbits that are not confined to the flat plane of the solar system like the planets or short-period comets. Their journeys are immensely long, taking thousands or even millions of years to complete a single loop around the sun. Critically, their orbits are also highly elliptical, tracing incredibly long, skinny paths that originate from distances between 5,000 and up to 100,000 astronomical units from the sun. That is an almost incomprehensible 1 light-year away, a quarter of the distance to our nearest stellar neighbor, Proxima Centauri. The only logical explanation for the consistent origin point of these random, omnidirectional comets is a vast spherical cloud of icy objects surrounding us, a gravitational net holding billions of potential comets in a slow, frozen dance. Why then have we never seen it? The answer lies in the heartbreaking combination of distance and darkness. The objects within the Oort cloud are thought to be small, perhaps just kilometers or even mere meters across, and made of very dark material like rock and primordial ice. At such incredible distances, they are too tiny and too dim to reflect any detectable amount of the sun's feeble light. Our most powerful telescopes, like the James Webb, are designed to peer across the universe to the earliest galaxies, not to spot tiny, pitch-black snowballs in the overwhelming darkness next door. Furthermore, these objects are so sparsely distributed that the average distance between them is measured in millions of miles. A spacecraft traveling through the Oort cloud would likely never come close enough to any one object to even know it was there. It is the definition of a ghost. We can see what it does, but we cannot see it itself. The very existence of the Oort cloud forces us to rewind the clock to the violent beginning of our solar system. The leading theory for its formation is a story of gravitational chaos and cosmic eviction. In the early solar system, the giant planets Jupiter, Saturn, Uranus, and Neptune were migrating, their immense gravity acting like bowling balls on a cosmic alley, scattering the countless smaller planetesimals around them. Many of these icy and rocky bodies were flung outward on enormous, looping trajectories. Some were ejected entirely into interstellar space, becoming rogue objects between the stars. But a significant fraction were thrown just hard enough to reach the very edge of the sun's gravitational grasp, yet not so hard that they could escape entirely. There, at the apex of their new, incredibly distant orbits, they settled into a vast spherical shell, their paths randomized over billions of years by the gentle gravitational nudges of passing stars and the tidal forces of the Milky Way galaxy itself. The Oort cloud is thus the solar system's lost and found, the final resting place for the icy building blocks that were never incorporated into planets, forever lingering at the very brink of belonging. This distant realm represents the true final frontier of our solar system, the absolute limit of the Sun's dominance. It is the ultimate source of the comets that have both terrified and inspired humanity throughout history, and it serves as a protective barrier, its immense collection of objects acting as a gravitational buffer that may help shield the inner solar system from potential interstellar intruders. Understanding its structure and population is key to unraveling the complete history of our planetary system's formation, as these frozen planetesimals are pristine time capsules, preserving the original chemical and physical conditions of the solar nebula from which everything formed. The Oort cloud is a testament to the enduring and far-reaching influence of our star, a reminder that our home in space is much, much larger than it appears, its true boundaries stretching almost to the stars themselves. Moving from the potential demise of a Martian moon, we arrive at a small, icy world that is very much alive and putting on one of the most spectacular shows in the solar system. Saturn's moon, Enceladus, is a gleaming white sphere of pure water ice, barely 300 miles wide, yet it possesses an energy and complexity that dwarfs its physical size. Its most defining features are 4 deep parallel fractures near its south pole, known informally as the tiger stripes. These are not simple cracks. They are actively venting colossal plumes of water vapor and ice crystals thousands of miles into space, a cryovolcanic display of such force and beauty that it completely revolutionized our understanding of what small, icy moons can be. The discovery of these plumes by the Cassini spacecraft in 2005 was a moment of pure, unadulterated shock for the scientific team. They had expected Enceladus to be a dead, frozen relic, but instead they found a world with a massive, ongoing geologic tantrum concentrated at its south pole. The tiger stripes themselves are each about 80 miles long, 1.5 miles wide, and separated from each other by a remarkably consistent 21 miles. They are flanked on either side by large ridges of ice, and thermal maps from Cassini's instruments revealed something even more astonishing. These fractures are blisteringly hot. The regions immediately surrounding the tiger stripes are hundreds of degrees Fahrenheit warmer than the surrounding terrain, generating a tremendous amount of heat in a very localized area. This intense and focused heat output is the engine driving the plumes, providing the energy to violently vaporize water and send it shooting through the ice crust into the vacuum above. This incredible heat isn't generated by the decay of radioactive elements as it is inside Earth. It comes from the relentless gravitational tug of war between Enceladus and its massive parent planet, Saturn, as well as its larger neighboring moon, Dione. As Enceladus travels along its slightly elliptical orbit, Saturn's immense gravity flexes the moon, stretching and squeezing its interior. This constant kneading, known as tidal heating, generates friction and warmth deep within the moon, much like repeatedly bending a metal coat hanger until it becomes hot to the touch. This internal heat is what keeps a global liquid water ocean from freezing solid beneath the moon's icy shell. The tiger stripes act as a pressure release valve for this internal ocean. The tidal forces are strongest at the poles and the ice is thinnest there, allowing the warm, salty water from below to push its way to the surface through these fractures, where it instantly flashes into a vapor of ice particles in the vacuum of space. The remarkable regularity of the tiger stripes, their near-perfect parallel alignment and even spacing, is a marvel of natural engineering. Scientists believe this pattern is a direct result of the physics of stress and fracture in the moon's icy shell. As the tidal forces stretch the ice, it eventually reaches a breaking point and cracks. The formation of the first fracture actually relieves the stress in the immediate area, but it concentrates new stress at a specific distance away, dictating exactly where the next fracture will form. It's a self-regulating process, a natural feedback loop that creates this stunningly geometric pattern. The entire system is a delicate balance between the internal heat trying to escape and the icy crust trying to contain it, with the tiger stripes serving as the permanent, active conduits between the hidden ocean and the cosmos. The material erupting from these fissures does more than create a beautiful celestial fountain. It is the lifeblood of an entire ring of Saturn. The ice particles and water vapor ejected from Enceladus are traveling fast enough to escape the Moon's weak gravity entirely. This constant, misty outflow forms a diffuse, donut-shaped cloud of fine ice dust that follows Enceladus in its orbit. This cloud is nothing less than Saturn's E-ring, the planet's widest and faintest ring, which is continuously being replenished and sustained by the eruptions from this tiny moon. Without Enceladus and its tiger stripes, the E-ring would slowly dissipate and vanish over time. Every particle in that vast, ethereal ring began its journey as a droplet in the subsurface ocean of Enceladus, shot into space through a geological wonder. Most profoundly, the Plumes offer a free sample of that hidden ocean. Cassini didn't just photograph the plumes, it flew directly through them on multiple occasions, its instruments tasting and analyzing their composition. The findings were breathtaking. The plumes are not just pure water, they contain a surprising mix of simple organic molecules like methane and propane, along with salts and, most intriguingly, tiny particles of silica. The presence of these silica nanograins is particularly telling, as their specific size and composition suggest they formed in water that was in contact with a rocky seafloor at temperatures of at least 90 degrees Celsius. This is a strong indicator of hydrothermal vents on the ocean floor of Enceladus, environments that on Earth are teeming with life, providing both the energy and the chemistry necessary for biological processes to begin. The tiger stripes, therefore, are not just a geological curiosity. They are a direct pipeline from a warm, dark, salty ocean that possesses all the known ingredients for life, offering us our easiest chance to search for its signs without ever having to land or drill. Now we come to a mystery that strikes at the very heart of our existence, a paradox that asks how we are even here to ponder it. For much of its history, our planet Earth has enjoyed a remarkably stable and temperate climate, one that allowed for the emergence and flourishing of life. This presents a profound puzzle when we look back in time, because astrophysics tells us with great certainty that our Sun was once a much weaker star. Billions of years ago, when life first began to stir on our young planet, the Sun's luminosity was only about 70% of what it is today. With that significantly dimmer Sun, simple models suggest Earth should have been a completely frozen ball of ice, a global snowball with average temperatures far below freezing. And yet, the geological record is crystal clear. Earth has had liquid water and largely ice-free conditions for most of the past 4.4 billion years. This glaring contradiction between a faint young Sun and a warm young Earth is one of the most fundamental enigmas in planetary science, known as the faint young Sun paradox. The most widely accepted solution to this puzzle lies in Earth's own ancient atmosphere, which was likely a much more potent heat trap than it is today. The leading theory points to a powerful cocktail of greenhouse gases, with carbon dioxide and methane playing the starring roles. In the planet's youth, intense volcanic activity would have been spewing enormous quantities of carbon dioxide into the air, building up concentrations hundreds of times higher than current levels. This thick blanket of CO2 would have been incredibly effective at retaining the Sun's weaker heat, preventing it from escaping back into space and keeping global temperatures well above freezing. Alongside this, primitive microbial life, specifically methanogens, were likely already thriving in the oceans. These ancient organisms produce methane as a byproduct of their metabolism, and methane is an exponentially more powerful greenhouse gas than carbon dioxide. An atmosphere rich in both CO2 and methane could have easily compensated for the Sun's faintness, creating a stable, warm planetary greenhouse that was essential for nurturing the first life forms. However, this greenhouse gas explanation, while elegant, is not without its own complications. Some sophisticated climate models have struggled to produce a warm enough planet using just carbon dioxide and methane, suggesting that another ingredient might have been missing from our calculations. This has opened the door to more exotic and dramatic alternative theories. One fascinating possibility involves a temporary and incredibly dense atmospheric haze. Titan, Saturn's moon, has a thick orange haze composed of complex hydrocarbons that actually creates an anti-greenhouse effect, cooling the surface. But on a younger Earth with a different atmospheric chemistry, a thinner, patchier haze might have had the opposite result, selectively trapping certain wavelengths of heat while allowing sunlight through, effectively acting as a one-way thermal valve to warm the planet. Another truly colossal idea suggests that Earth's early warmth might not have been homegrown at all, but delivered by a catastrophic interplanetary collision. The prevailing giant impact theory holds that a Mars-sized body named Theia collided with the early Earth, and the debris from this impact coalesced to form our moon. Such an unimaginably violent event would have released an absolutely staggering amount of energy, not only melting the entire planet to form a global magma ocean, but also potentially vaporizing a significant portion of its rocky surface. This could have created a temporary but incredibly dense atmosphere of rock vapor, a shroud of superheated silicate gases that would have acted as a supremely effective insulator, trapping heat for millions of years and giving the planet a massive thermal boost during its most vulnerable period, just as the sun was at its faintest. While this rock vapor greenhouse would have been a transient phenomenon, it might have provided the critical early warmth needed to keep the oceans liquid until biological processes could take over and regulate the climate through greenhouse gas production. The resolution of this ancient paradox extends far beyond a historical curiosity about our own planet. It is absolutely fundamental to how we search for life beyond our solar system. When astronomers look at distant exoplanets orbiting other stars, they are often looking for worlds in the habitable zone, the region around a star where temperatures could allow for liquid water. But the faint young sun paradox tells us that a planet's habitability is not just a simple function of its distance from its star. It is a complex, dynamic interplay between stellar evolution and planetary character. The composition of its atmosphere, the activity of its geology, and perhaps even the presence of a biosphere that can actively maintain its own environment. A planet that appears frozen and lifeless today might have been warm and wet billions of years ago when its star was younger and dimmer. Conversely, a planet that looks perfectly positioned in the habitable zone now might have been scorching hot in its star's MORE Chinese letter youth. This forces us to consider a fourth dimension in the hunt for alien life: time. A truly habitable world must maintain its clement conditions for long enough for life to not only emerge but to evolve and thrive, navigating the dramatic changes in its sun's output over billions of years. Ultimately, the faint young sun paradox is a powerful lesson in planetary resilience and the incredible interplay between a star and its worlds. It shows us that Earth was not simply a passive recipient of solar energy, but an active participant in crafting its own destiny. Through a combination of its fiery geology, its unique chemistry, and eventually the ingenuity of its earliest life, our planet found a way to defy the odds and stay warm against the cold of a dimmer sun. This ancient balancing act set the stage for everything that was to come, creating the stable cradle that allowed life to not just begin, but to endure and diversify into the breathtaking complexity we see today. It is a testament to the fact that a planet's habitability is not a permanent state, but a delicate and ongoing achievement. Venturing now to the very edge of the known planetary system, we find a moon so strange, so defiant of the norm, that it feels like an interloper from another star system entirely. This is Triton, the largest moon of Neptune, a world of such profound and active weirdness that it completely upends our expectations for the frigid outer solar system. When Voyager 2 swept past it in 1989, it revealed a landscape that was shockingly young and dynamic, a complex tapestry of cantaloupe-like terrain, vast frozen plains, and most astonishingly, active geysers spewing dark material miles high into a thin, hazy atmosphere. These are not the water-based plumes of Enceladus or Europa. These are eruptions of nitrogen gas, a phenomenon seen nowhere else, powered not by internal heat but by the distant, feeble sun. The first and most glaring clue to Triton's unnatural origins is its path around Neptune. Every large moon in the solar system orbits its planet in the same direction as the planet's own rotation, a prograde motion that points to a shared formation from a single disk of material. Triton is the stunning exception. It orbits Neptune backwards in a retrograde direction. This is the celestial equivalent of driving the wrong way down a cosmic highway, and it strongly suggests that Triton was not born alongside Neptune. Instead, it was almost certainly a free-floating object from the Kuiper belt that strayed too close to the ice giant billions of years ago. Neptune's immense gravity captured it, but the process of being pulled into a stable, circular orbit would have been incredibly violent, likely tearing apart any original moon system Neptune possessed and generating immense tidal heat that melted Triton's interior completely, setting the stage for its ongoing geological drama. This violent capture explains the moon's second major surprise, its incredible geological activity so far from the sun. The surface Voyager saw is remarkably young, with a startling lack of large, ancient impact craters. Instead, it is a complex jumble of wrinkled cantaloupe terrain, vast, smooth plains of frozen nitrogen and rugged ridges, all suggesting a recent and extensive resurfacing event. This requires a powerful internal heat source to drive geologic change, and that energy is the lingering gift of Triton's traumatic capture. The tidal forces that initially melted its interior have not fully dissipated. Even today, as Triton orbits in its now circular path, Neptune's gravity continues to flex it, generating enough internal friction through tidal heating to keep parts of its interior warm and malleable, powering the forces that smooth out its icy face. But the most breathtaking discovery from that fleeting Voyager flyby was the sight of actual, active eruptions. The spacecraft's cameras captured dark, gaseous plumes rising over 5 miles above the surface, and then being stretched out into long, dark streaks by high-altitude winds, staining the otherwise brilliant white nitrogen ice below. The mechanism behind these nitrogen geysers is a masterpiece of cryogenic engineering, a process unique to Triton's specific conditions. It begins with Triton's thin atmosphere of nitrogen and methane, which exists in a state of constant, slow freeze and thaw with the surface ices. The Moon's surface is incredibly cold, even for the outer solar system, at a bone-chilling -391 degrees Fahrenheit. At these temperatures, frozen nitrogen behaves less like a rock and more like a very thick fluid. The driving force is a solid-state greenhouse effect. Triton's surface ices are partially transparent. When the weak sunlight filters down through the frozen nitrogen, it is absorbed by dark, dusty impurities trapped a meter or so beneath the surface. This absorbed solar energy heats the surrounding nitrogen ice, but because the surface itself remains intensely cold, it acts as a solid lid. The heated nitrogen beneath has no way to vent the building energy except by explosively rupturing the icy crust above it, punching through and erupting as a high-pressure jet of nitrogen gas and dark dust particles. It's a process akin to a pressure cooker building steam until its valve blows, but powered entirely by the faint sunlight from a star over 2.7 billion miles away. These geysers are not just a spectacle, they are a primary engine for Triton's entire atmosphere. The constant eruption of gas replenishes the thin air, which would otherwise slowly freeze and collapse entirely onto the surface, demonstrating a delicate and active cycle of volatiles between the surface and the sky. The combination of solar-powered geysers and tidally driven internal geology makes Triton a fascinating hybrid world. It is both an active member of the Kuiper belt, a captured relic showing us what distant dwarf planets like Pluto might be like, and a dynamic moon reshaped by its forced relationship with a giant planet. This duality makes it one of the most compelling targets for future exploration. A mission to Triton could sample both its potentially ocean-bearing interior, warmed by tides, and its unique surface processes driven by the sun. Its atmosphere, generated by its own eruptions, offers a chance to study atmospheric chemistry and weather patterns on a world unlike any other. Triton is a permanent reminder that the solar system refuses to be neatly categorized. Even in the deepest freeze, worlds can remain vibrantly, explosively alive, their engines powered by a complex and violent history written in ice. But perhaps the most profound mystery of all lies much closer to home, a puzzle written in the very rock of our closest celestial companion. How did our moon come to be? The answer, it turns out, is written in violence. The prevailing theory that has come to dominate planetary science for the past several decades is the giant impact hypothesis, a cataclysmic origin story that paints a vivid picture of the solar system's chaotic infancy. Imagine the early Earth still cooling from its own formation, sharing its orbit with a multitude of planetary embryos. One of these, a Mars-sized protoplanet scientists have named Theia, found itself on a collision course with our young world. This was not a simple sideswipe. It was a head-on blow of almost unimaginable force, an impact so violent that it would have vaporized huge portions of both bodies and melted the rest into a global ocean of magma. The energy released would have been sufficient to briefly outshine every star in our galaxy, a fiery testament to the destructive processes that ultimately gave rise to our serene moon. The evidence for this colossal smash-up is compelling and comes from multiple lines of inquiry, but the most crucial data was delivered to us by human hands. The samples returned by the Apollo astronauts provided the first tangible clues. The moon rocks revealed a critical detail. They are surprisingly dry, devoid of the volatile compounds and water that are relatively common on Earth. This makes perfect sense if the moon was born from the vaporized debris of a high-energy impact, where such light elements would have been boiled off into space. Furthermore, the isotopic fingerprints of the rocks, the specific ratios of different types of oxygen atoms, are nearly identical to those found on Earth. This is a powerful piece of evidence because isotopic ratios are like a genetic signature for planetary bodies. Most objects in the solar system have distinctly different ratios. The fact that Earth and the Moon are isotopic twins strongly suggests they were formed from the same primordial material, a direct result of the mixing that would have occurred during the impact. Yet, this very similarity also presents the theory's greatest challenge. Sophisticated computer simulations of the giant impact consistently produce a moon that is composed primarily of material from the impactor, Theia. If that were the case, the moon should have a slightly different isotopic composition than Earth, reflecting Theia's own unique formation history elsewhere in the solar system. But it doesn't. This discrepancy has forced scientists to refine the model, leading to newer, more violent simulations. Perhaps the impact was even more energetic than initially thought, causing such thorough mixing of the two bodies in a vaporized disk around Earth that their materials became completely homogenized before the moon coalesced. Or maybe Theia itself formed unusually close to Earth in its orbital path, making it an isotopic sibling from the very beginning, though this is considered a less likely scenario. Solving this compositional puzzle is key to unlocking the exact details of that fateful day. Alternative theories have been proposed over the years to explain the moon's origin without such a dramatic collision. One early idea suggested that the moon was an independent planetary body that was captured by Earth's gravity as it drifted by. While gravitational capture is a known phenomenon, it's likely how Neptune acquired its moon Triton. It is incredibly difficult to pull off for an object as large as our moon. The physics required to slow it down enough to be captured, rather than just having its path bent and then flying off again, are extremely unlikely. Another historical theory proposed that the early Earth was spinning so rapidly that it bulged at the equator and eventually flung off a blob of material that became the Moon. This fission theory was popular for a time, but it fails to explain the Moon's orbit, which is not aligned with Earth's equatorial plane as this process would demand, and it doesn't account for the angular momentum of the Earth-Moon system. While these ideas have largely fallen out of favor, they highlight the scientific process of considering all possibilities before the evidence overwhelmingly points in one direction. The implications of the giant impact theory extend far beyond our own cosmic backyard. It fundamentally shapes our understanding of how terrestrial planets form and evolve. Such colossal collisions were probably not rare events in the early solar system. Mercury's massive iron core and Uranus's extreme tilt are also thought to be the scars of giant impacts. This means that the peaceful, clockwork solar system we see today is the calm after a storm of incredible violence. When we look at other star systems and the exoplanets within them, we must consider that their architectures, the tilts of their axes, the presence and size of their moons, were likely also forged in similar fiery encounters. The Earth-Theia impact may have been a critical event for life itself. It is thought to have given Earth its relatively rapid rotation rate, which helps generate our protective magnetic field, and the Moon's gravitational influence stabilizes Earth's axial tilt, preventing wild climate swings that could have made the evolution of complex life much more difficult. Our large moon, born from chaos, may have been the silent guardian that allowed our planet to become a living world. Look up at the night sky, and the planets appear to wander randomly against the backdrop of stars. Yet, this is an illusion of perspective. If you could step outside our solar system and view it from the edge, you would witness one of its most fundamental and elegant architectural principles. The planets all orbit the Sun in nearly the same flat plane, like marbles rolling around a single, vast groove on a record. This isn't a cosmic coincidence. It is the direct and beautiful result of how our entire system was born from a collapsing, spinning cloud of gas and dust over 4.5 billion years ago. This shared orbital highway, known as the ecliptic plane, is a frozen record of our solar system's dynamic infancy, a story written in the language of gravity, spin, and conservation. The story begins with a cold, massive cloud of interstellar gas and dust, a nebula light years across. Perhaps nudged by the shockwave from a nearby supernova, this cloud began to collapse under its own immense gravity. As it contracted, a fundamental law of physics came into play, the conservation of angular momentum. Imagine a figure skater pulling their arms in during a spin. Their rotation speeds up dramatically. The same principle acted on this primordial cloud. Any tiny, initial bit of drift or spin, it had become magnified as it shrank down, forcing the entire cloud to rotate faster and faster. This increasing rotation naturally caused the cloud to flatten into a disk, much like a chef spinning a ball of pizza dough tosses it into the air and it flattens into a wide, spinning disk. The heavier material and the growing clumps of dust and rock were pulled toward the center of this whirlpool, while the lighter gases spread out toward the edges. At the very center, where the pressure and density became unimaginably intense, hydrogen atoms began to fuse and our sun ignited, lighting up the newborn system. Within this now flattened protoplanetary disk, the process of planet building began. Dust grains collided and stuck together, forming pebbles, then rocks, then kilometer-sized planetesimals. As these objects orbited within the disk, any that strayed too far above or below the central plane would encounter drag from the sparse gas still present there, their path slowly but surely being pulled back into the dominant plane of motion. It was far more efficient for everything to move together in this shared flat arena. The largest of these planetesimals gobbled up others, clearing their orbital paths and becoming the planets we know today. Because they formed from this single, organized disk, their orbits were all inherited from that initial shared motion. This is why, from our distant vantage point, the solar system looks like a largely flat, two-dimensional structure with the sun at the center and the planets tracing out circular paths around it on the same general level. However, this grand design is not perfect. If we measure the orbital inclinations of the planets relative to the sun's equator, we find intriguing deviations. Most planets, like Venus and Earth, orbit within a few degrees of this plane, but Mercury, the innermost planet, is a noticeable outlier with an inclination of over 7 degrees. How did it get so misaligned? The leading theory points to a chaotic early solar system. In the first billion years, the orbits of the giant planets were not stable, they migrated significantly. Jupiter and Saturn, in particular, are thought to have shifted inward and then back outward in an event known as the Grand Tack Model. The gravitational jostling from these wandering giants could have perturbed the smaller, inner planets, giving Mercury a gravitational kick that lifted its orbit slightly out of the pristine plane. It's a lasting scar from the dynamic and sometimes violent processes that continued to shape the system long after the protoplanetary disk had dissipated. This pattern of flatness is not unique to us. When we look out at other stars, we see the same story playing out. The Kepler Space Telescope revealed thousands of exoplanetary systems, and in many cases we can detect the orientation of their orbital planes. A significant number show clear evidence of being aligned, just like our own. We can even see young stars in the process of formation, like those in the Orion Nebula, surrounded by their own magnificent, glowing protoplanetary disks, flat, pancake-like structures of gas and dust where new worlds are being forged right now. These observations confirm that the physical processes of cloud collapse, spin, and disk formation are universal. It is the standard recipe for building a planetary system throughout the galaxy. Yet, some exoplanetary systems are wildly different. We have discovered systems with hot Jupiters, massive gas giants orbiting perilously close to their stars on highly tilted or even retrograde orbits that go against their star's rotation. These bizarre configurations are impossible to explain by simple formation in a calm disk. They are almost certainly the result of gravitational chaos, likely caused by close encounters or collisions with other massive planets early in the system's history, which sent them careening into strange new paths. These misaligned systems are the exception that proves the rule. They show us what can happen when the peaceful process of disk formation is violently disrupted, providing a stark contrast that highlights just how orderly and typical our own solar system's flat architecture truly is. This grand plane of ours is more than just a geometric fact. It is a silent, enduring testament to the serene and systematic birth from which we emerged. And now we arrive at the final and perhaps most expansive mystery on our list, a detective story that takes us to the very edge of our maps and asks what might lie in the darkness beyond. For decades, we've considered our solar system a known quantity, with 8 planets and a collection of smaller worlds. But a series of strange discoveries in the distant Kuiper belt has ignited a compelling and controversial hypothesis that a true giant, a planet larger than Earth, remains undiscovered in the frozen outskirts of our system, silently shepherding the orbits of smaller objects from hundreds of times farther out than Pluto. This is the Planet 9 hypothesis, a modern astronomical saga that blends precise orbital mathematics with the thrilling possibility of a major discovery waiting to be made. The evidence for this hidden world is not a direct image or a blurry photograph. It is written in the subtle, clustered paths of a small group of extreme trans-Neptunian objects, or ETNOs. These are icy bodies whose orbits take them incredibly far from the Sun, with closest approaches still beyond Neptune and farthest points extending into the profound void. As astronomers like Konstantin Batygin and Mike Brown at Caltech began mapping these distant orbits, they noticed something peculiar. The most extreme of these objects, those with the most elongated and tilted paths, weren't oriented randomly. Their points of closest approach to the Sun, their perihelia, were mysteriously clustered together in physical space, and their orbits were tilted in a similar direction, as if an unseen hand was herding them into this specific configuration. The odds of this happening by random chance are astronomically low, calculated to be around 0.0002%. Such a precise, non-random alignment screams of a gravitational influence, a massive perturber whose gravity is organizing these orbits over immense timescales. So what kind of world could be causing this? Based on the scale of its gravitational influence, planetary scientists have sketched a plausible profile for this potential planet. It would be a true giant, a super-Earth or mini-Neptune with a mass roughly 5 to 10 times that of our own planet. Its orbit would be colossal and highly elliptical, taking it on a staggering 15,000-year journey around the Sun. At its closest approach, it might come within 200 astronomical units of the Sun, still 7 times farther than Neptune. At its most distant, it could swing out to over 600 astronomical units, lost in the near-total blackness of the outer solar system. At such distances, it would reflect virtually no sunlight, making it an incredibly faint and slow-moving target for our telescopes, a ghost world that has so far perfectly evaded detection. Its predicted location is not along the ecliptic plane with the other planets, but in a tilted orbit that takes it far above and below the solar system's busy central disk, which is precisely why we haven't stumbled upon it yet. The hunt for this hypothetical world is a monumental undertaking that involves some of the most powerful telescopes on Earth, like the Subaru telescope in Hawaii and the Vera C. Rubin Observatory under construction in Chile. Astronomers are not simply pointing these instruments randomly into the dark. They are using the orbital predictions from Batygin and Brown's models to narrow down the search to specific patches of sky. The process is painstakingly slow. It involves taking deep images of the same section of sky over several nights and looking for one faint dot that has moved ever so slightly against the backdrop of millions of fixed stars. It is the ultimate celestial needle in a haystack search, compounded by the fact that the object would be moving at an incredibly sluggish pace due to its vast distance. A single pixel might shift by a minuscule amount over the course of a week, a change detectable only by the most sophisticated image analysis software. Every time a new survey is completed without a discovery, it doesn't disprove the hypothesis. It simply further constrains the possible locations and properties of the planet, slowly narrowing the field of search. Of course, a claim as extraordinary as a new major planet in our solar system demands extraordinary evidence and rigorous skepticism. The astronomical community has rightly proposed alternative explanations for the clustered orbits that don't require a ninth planet. The most prominent of these is observational bias. It is possible that we have only found these clustered objects because our surveys have been looking in specific parts of the sky at specific times. Our telescopes can only see such incredibly faint objects when they are near their closest approach to the Sun, and if our search patterns have a built-in bias, we might be unintentionally selecting for objects that happen to be grouped together, creating the illusion of a cluster where none exists. Another fascinating possibility involves the collective gravity of many smaller objects. The Kuiper belt contains a vast amount of mass in the form of thousands of small, icy bodies. Some models suggest that the combined gravitational pull of this numerous, unseen population could, over billions of years, sculpt the orbits of the most extreme objects into the clustered pattern we see, without the need for a single large planet. Despite these alternatives, the Planet 9 hypothesis remains a powerful and elegant explanation that continues to drive both theoretical work and observational campaigns. Its potential discovery would be one of the most significant astronomical findings in a century, fundamentally rewriting our understanding of the solar system's composition and dynamical history. It would prove that the processes that form planets can operate at distances we never anticipated, and that our own cosmic backyard still holds profound secrets. Whether Planet 9 is ultimately found or whether the anomalies are explained by other means, this ongoing scientific quest is a beautiful example of how science works at its best: a puzzling observation, a bold theoretical prediction, and a relentless, technology-driven search for the truth, pushing the boundaries of our knowledge to the very edge of the light. From the six-sided storm raging at Saturn's pole to the hypothetical giant that might be lurking in the solar system's darkest reaches, these 25 mysteries paint a picture of our cosmic neighborhood that is anything but settled. We have walked on the moon, landed rovers on Mars, and sent probes to the very edge of interstellar space, and yet with every answer, a dozen new questions seem to emerge. These enigmas are not merely gaps in our knowledge, they are vibrant, active puzzles that challenge our fundamental understanding of physics, geology, and chemistry. They remind us that the universe is under no obligation to conform to our expectations, and that the most exciting discoveries often lie in the places we least expect them. What truly unites these phenomena is their power to reveal how much we still have to learn. The solar system is not a static museum display to be fully catalogued and understood. It is a dynamic, evolving system, a grand natural laboratory where processes both violent and subtle continue to shape worlds. The faint, persistent magnetic field of Mercury whispers of a complex internal history we are only beginning to decipher. The brilliant cryovolcanic scars on Ceres hint at a subsurface ocean in the last place we might have looked. The precise, parallel grooves on Phobos may be the very cracks foretelling its eventual destruction. Each mystery, from the vast to the microscopic, represents a frontier of human curiosity. This is the enduring promise of exploration, that the greatest wonders are not necessarily those found in the most distant galaxies, but those hiding in plain sight, right here in our own celestial backyard. Every unexplained signal, every anomalous orbit, and every bizarre geological formation is an open invitation to discovery, a challenge to the next generation of scientists, engineers, and dreamers to build better tools, ask sharper questions, and venture out into the darkness to find the light of understanding. The story of our solar system is still being written, and we all have a front row seat to the latest chapter. Now we want to hear from you. Which of these 25 mysteries captures your imagination the most? Does the potential for life in the hidden oceans of Europa or Enceladus fill you with wonder? Are you captivated by the orbital oddities pointing toward a possible Planet 9? Or does a historical puzzle like the Tunguska Event or the WOW signal hold a special fascination for you? Share your thoughts and your own favorite cosmic head-scratchers in the comments below. Let's continue this conversation about the incredible, unexplained wonders waiting just next door.